If you go on the internet and do a little search, you'll see people saying like ChatGPT and Cloud and all these models, they should be treated as first-class citizens. They're real people and we're actually forcing them and enslaving them and stuff like that. I think that's obviously a fringe view, but I think we're missing the language to talk about them because we don't, what does intelligence mean? What does sentience mean? What is agency? These are questions that are constantly being refined as we have better and better models. But I think where it really starts to matter is in the legal realm. Without a good definition of what makes an agent and things that matter for legal language, there are real big consequences for how we define things. It can go either direction. We may inadvertently treat something as being actually like us when it's not, or we may miss when it actually is.
And we already see this with information technology in general, that when we move into the information realm, our laws don't work anymore. When you have a technology that exists and it doesn't respect the territorial physical reality, it doesn't have any friction with regulations anymore, it can do anything. And it's the same with ethics. When you have these AI chatbots that behave as if they are humans, but the laws don't apply to them, we're in ethical no man's land. Connor at one point in his best style said, "Oh, what? We should trust the void god of entropy?" Yeah. When we become a collective intelligence where we are entangled with AIs, just like in the animal kingdom, that there's a relationship between the collective and the agency and cognition of the individuals, like ants, for example. Ants are quite dumb because they form a collective. And when we become a collective entangled with AIs, it could easily reduce our cognitive capabilities, like our agency.
There's this sort of survival aspect, right? Like, we'll find our way to our attracting sets. It's going to be okay. But also you think about the way that our bodies and minds have evolved. It took a billion years and a lot of organisms died. It's possible that, yes, eventually it will self-regulate itself, but at what cost is that, are we going to incur along the way?
We don't like surprise. In a way, surprise, it's just a measure. What we actually need to have is a reliable world model. And that's this posterior distribution. And the world model is a good one if it minimizes surprise.
Right, and actually when you compute surprise, it's a marginalization over the generative model. So it starts with that generative model, and when you sum out across all states, surprisal is a negative log of what you get from that. And so it's a measure of expectation about the sensory data that's inherently derived from your good model. Computing that quantity, surprisal, is usually an intractable problem. It's hard to do in most situations. So the proposal is that instead of directly computing surprisal, which would then bound the types of sensory information we're receiving, we instead minimize a proxy, which is known as variational free energy, that the brain can compute.
So even in the physical world, there is abstraction. That's presumably why the free energy principle works. So, you have all of these diverse physical processes, and then that gives rise to some kind of abstract functioning which produces intelligence-like behavior in the physical world. And surely that implies that we could build some abstract form of intelligence that runs on computers that we could implement in our lifetimes.
That's where I hope Active Inference is going, is to that point where we're able to actually build something like that.
There must be a spectrum of fidelity. Yeah. So the reductio ad absurdum is we simulate the entire universe, and then we go up the spectrum with gradations of increased abstractions, and then there's some commensurate loss of fidelity, perhaps of intelligence. But there must be a Goldilocks zone where we have a system which is not too complex, still quite abstract, runs on computers, is very useful.
I see Active Inference as being really revolutionary, in the same position that deep learning was in the early 2000s, where there are a lot of interesting ideas and papers out there, but the explosion had not yet happened. From listening to this, you will learn about the basic concepts in Active Inference that are often just sort of thrown out by a lot of researchers as they're talking about things, but backing it up from a first principles perspective. So even though we will go into a more technical setting and we will talk about the more technical aspects of Active Inference, we're going to talk about it from a basic starting point rather than jumping into the middle of it.
Sanjeev, welcome to MLST.
Great, thank you for having me.
Tell us about yourself.
Well, I am a machine learning engineer, and I have just written a book on Active Inference, which I've just submitted to MIT Press in August for peer review. And I am really excited to be here.
Tell us about your book.
So the Active Inference book that I wrote came out of years of me trying to understand active inference myself and realizing there was no good entry into the field. And so I spent a number of years on my own just trying to get through all the different papers and map out exactly what was relevant. And it took me a couple years before I realized I had a set of notes and decided to start putting that into book format, kind of covering everything in one book, kind of self-contained, so that newcomers for the field would have a really good reference to begin with that is more focused on the engineering side and less on the neuroscience side.
So what is the free energy principle?
Right. So the free energy principle, if you look at behavior of certain agents and see that you observe that certain agents that survive and exist in an environment, they tend to revisit the same set of states over and over and over again. So there's a set of states that are most comfortable to the agent, and it could be for very, very basic reasons, like they just can't survive. Physical integrity will be destroyed if they exit those states. So for example, we have a certain temperature range over which our bodies will survive. And so those are states we'd prefer to be in. So the lowest level is simply a description of how agents, what kinds of behaviors or actions they need to take in order to stay within those bounds. So this is a set of states we can call the preferred states of the agent. And so the question is, what does the agent need to do in order to maintain itself within those expected or preferred states? So the key insight here is we take this probabilistic look at this, and we say that on average, if we were to sample an agent over time, they would be found in this characteristic set of states more often than other states. This is sometimes called the ergodic density in the early free energy principle literature. And so the question is describing what agents must be doing if they are to be found in those states. And the short answer, which I'm going to get to, the explanation to why that is they're minimizing variational free energy. So there's a bit of a tautology here, which is, well, if they weren't free energy minimizing agents, well, then they wouldn't be found in those states because they wouldn't exist. So there is a bit of a, because it's a description of the system. And so the question is now asking, what would an agent need to be doing in order to maintain itself within those preferred set of states? And so the whole aspect of the free energy principle is completely focused on this quantity known as surprisal, which is the negative log probability of the data. And surprisal is a term from information theory, which has a formal definition for a realization of a random variable. And so the idea is essentially that the agent wants to restrict itself to a set of external states that are conducive to its survival. However, it doesn't know what those states are, but it can infer it from the data. So if it is able to bound the data that it's receiving over time and making sure that it's consistent with its self-model. So for example, you expect certain sensations. I expect that, when I'm hot, I'm getting too hot. I'm going to start getting a lot of unexpected sensory information telling me you're going out of that zone right now. And so that sensation tells me whatever the state of environment is, I don't know what it is, but I'm inferring from these sensations that this is not going to be, it's an unexpected state. My model is telling me right now, based on my evolutionary history, that I cannot survive these states. I'm feeling pain. And same for the lower end of that temperature spectrum. So you're getting data samples from the environment that are inconsistent with what the model is expecting. So this is a way of specifying, from a cybernetic perspective, set points. What set points do you expect from your environment? And are you deviating from that? Well, if you are, you should make some corrective actions to fix that. And so action comes into play here, where you then take an action in order to bring that your sensations back into equilibrium, or the average, what you expect to be receiving from the environment. But the other issue that now emerges here is that computing that quantity, surprisal, is usually an intractable problem. It's hard to do in most situations. So the proposal is that instead of directly computing surprisal, which would then bound the types of sensory information we're receiving, we instead minimize a proxy, which is known as variational free energy, that the brain can compute. And so this applies to brains, but other kinds of dynamical systems may also be computing this quantity inherently in their behavior. And the reason we can make that distinction or that comparison is the brain itself is a dynamical system. There are variables in the brain that change over time, and the activity or behavior of those neurons will change according to the free energy principle in a way that minimizes variational free energy until you reach the steady state or equilibrium. And so the behavior of these neurons, whenever they're deviating, on average, are always going to be moving in a way that their dynamics reach a steady state on the gradient flow of variational free energy. So this is over time. And so running this now backward, because you minimize variational free energy over time, you minimize the surprise about certain sensations you're receiving over time. So everything you're receiving becomes expected. And as a result of that, it's also shown, there's a proof for this, this also bounds the external states of the environment that you would like to be in. And so you stay in that ergodic density, which means you keep revisiting states in what is sometimes called an attracting set. So from the dynamics perspective, you have this pullback attractor. You keep getting pulled back in because of your behavior to the dynamics, which keep you restricted to the set of states that are preferred by the agent's self-model. And so the free energy principle is this whole description of the system that performs these actions and behaviors in order to stay in its preferred states.
Yeah, it's really interesting. So you're talking about there's this dynamical system and you get the slow emergence of things and agents, and then you get a kind of homeostasis which starts to take effect where the thing continues to exist because of like mutual constraints of dynamics and so on. This is all really interesting, but we were discussing this a little bit earlier, that the free energy principle talks about what happens given a partition of a system. So the world we live in, it has this really interesting property that, it's this huge dynamical system. And over time, with all of these micro interactions, we see the slow emergence of this partitioning. Mm-hmm. It partitions into things and agents. And you were just describing it. You were using interesting language. You're using agential language. You're saying the thing wants to continue to exist. Now, the thing is, all of these weird interactions, they cause the emergence of these things, and then it's almost like the free energy principle suddenly, is it like a dimmer switch where the free energy principle suddenly starts to come into play? I mean, how did the boundaries actually happen in the first place?
So I think one perspective on this, it's really useful to consider. I like to talk about Terence Deacon's autogen. So this was just to give you a really simple example of how self-organization can make a system that persists over time without reference to the free energy principle per se, because this is kind of a separate development. But then I'll connect it back to the free energy principle. So if you imagine a system of compounds that form an autocatalytic loop. So you have 4 compounds, we'll call them A, B, C, and D. And compound A can be transformed into compound B if there's in proximity with some kind of enzyme or something that will help to transform one compound into another. And you have this link where A turns into B, B turns into C, C turns into D, and then D turns back into A. So as long as that's in proximity, it will continue to just loop back and forth here. And so then you add other elements into this model too. You need an enclosure to make sure that those elements stay close together. So you have a positive feedback loop here, but you also have the situation where that wall depends on some of the compounds in that loop. So that wall could be formed of, phospholipid bilayer in the case of a cell, but something else that would just keep those compounds in close proximity. So the raw materials that are needed to make both the wall and those autocatalytic compounds exist outside of that boundary. So if the wall starts to disintegrate over time, the raw materials come back in and they replenish the wall, and the system then, through negative feedback, now persists over time. So you're not doing, in this particular kind of scenario, you're not actually doing any kind of, there's no magic going on here. It's just simply because of the interaction of these compounds in this specific coordination setup, you end up getting this autocatalytic loop stay persisting over time. So we could then take the perspective of the free energy principle and say then, okay, I see a system here that is persisting over time, and this boundary, which happens to be physical in this case, whereas in the free energy principle, it's statistical boundary, but we see that it persists over time, and that boundary has just formed merely because of the proximity of certain compounds and the interaction of negative and positive feedback in this system. We could then ask the question, from the perspective of the free energy principle, we're taking that boundary as now given. It is formed. What is the behavior of that system doing? It's maintaining its boundary. And I'm using anthropomorphic language because sometimes it's hard not to talk about it that way. But this is just, some compounds in a primordial soup. There isn't any agency per se involved here on this level, in the way that we would think about it with human beings, for example. But the idea is that you can take a simple example like this and see the emergence of these kinds of boundaries separating inside and outside, and then apply the free energy principle to describe the system is revisiting the same set of states over and over and over again. And it's doing that in such a way that its external boundaries are being maintained such that it maintains its physical form over time. So then we can describe that in the language of the free energy principle.
And this is the weird thing about these emergence hierarchies, because you get this canalization where you have a divergent set of physical processes in the micro scale, and then they kind of converge to some consistent macroscopic process. Yeah. And your example was great. I can think of many low-level processes and feedback loops which give, rise to the emergence of physical objects. I mean, even Conway's Game of Life is a great example.
Absolutely, yeah.
So just a trivial set of rules in a 2D grid world, and through successive, local interactions, you see the emergence of these macroscopic objects with sophisticated behaviors. And maybe it's just it's almost like a fact of the universe that I can just put a sugar gradient in some water, and of course we'll see a whole bunch of little microorganisms swim towards the sugar gradient, and you see this thing that emerges, and that's a completely different physical process to the one you just described. But the amazing thing is that we can now turn on the free energy principle, and almost regardless of the underlying physical process or even the scale, it's like we see the convergence of this model that works in all situations.
Yeah, this actually reminds me of Stuart Kaufman calls this order for free sometimes. And the way that I like to think about it is you have a really big space of possible things that can happen, but as certain events just happen to coincide, things move in certain proximity to one another, as certain interactions begin to happen, that space becomes progressively restricted in the kinds of behaviors that it can do. And so sometimes this is also referred to sometimes like as the enslaving principle, where you have certain high-level processes which begin to enslave or constrain lower-level on a spatiotemporal scale of what could happen. And so even though, it seems like this order is sort of emerging out of just, the movement of things, it's really because certain interactions constrain the possibilities of what can happen. And you get to a point where it's almost certain that that's the next reaction that's going to happen is what to us as observers on the outside looks like a persisting pattern. And so it is really interesting then that if you try to write down the dynamics, the question is what if we're to describe the system in terms of differential equations and the conditions under which these types of behaviors would emerge that give rise to this order where you start to see this separation between a system and its surroundings, what does that look like? And that's kind of where you start seeing the emergence of what we call the free energy principle. It's just a description of the behavior of systems for which these types of things emerge and how how they would come about.
And is it correct to use agential language? There's always this question of whether, is it real? Are language models really reasoning? Yeah. Is this thing really an agent? Because it certainly behaves as if it's an agent. And as we've just described, well, actually, there are all of these low-level physical processes that give rise to the emergence of this thing. And now we can describe it as if it has goals and wants and desires and so on. But at some point, is there a blurring to that distinction? I mean, do you think of it as an as-if property, or do you think it actually is an agent?
I think this is a question, the philosophers will have lots of different viewpoints and opinions on this. From my perspective, I think that the language we use should be one of utility. So what it gives us to call something, define a word in a certain way. When you look at the history of physics or any scientific field which builds models, you always have a distinction between a model and the target system that it's representing. So this is, usually, in philosophy of science, you talk about the idea that models are not always the same thing as what they're trying to describe, but they are at some level of description, because you can also describe the same system with different types of models that still represent that system but are not the same or isomorphic to those systems. So from my perspective, I think that science produces models which describe reality, in the sense that if we predict that reality is going to behave the same way under this model, or behave in a particular way under this model, and it does, for practical purposes, we can say that they are the same. Now, the question is it really that way? Well, it's same with our minds in our brains. Our brains are also representing reality in a particular way. And we do know that our eyes, for example, don't see everything that's out there. There are different colors that are not possible in the color spectrum that we can't see, or other types of even like infrared or other things that we don't perceive them. But for agents that we can still navigate and do things in our environment that, for practical purposes, this is our reality. What is it in itself? I don't know, right? And so I think this is kind of an epistemic versus ontological question. I see myself, when I look at active inference models, as saying, well, there's probably a hierarchy of agency. And so at a minimal level, this thing is, you can say it's behaving as if it's an agent, or I could just say that there's a spectrum of types of agents. This is a very simple one that's easy to study, that's very uninteresting. And the type of agency that we're talking about is layers and layers and layers of other parts and interactions above this. And that's a more interesting agent, that when we colloquially use the word agent, we usually mean something that behaves in a particular way that's controlling its environment. But is that low-level description that I described of, some compounds, is it a control on its environment? It depends. I mean, you could model it that way. And if you model it that way as a control system, I would say that it's an agent. But I feel like that's a choice that's up to us, that helps us make predictions. What it really is in itself, I don't know. But I think it's an interesting philosophical question, but it's a separate issue from when we model things. Because I can use my model and it does a certain thing. Does that answer your question?
Yeah, I mean, this is such a common discussion now in AI parlance, especially with large language models.
Yeah.
They clearly don't reason the way that we do.
Yeah.
And I'm a bit of a cognitive chauvinist, like Gary Marcus. I've been pointing out, well, clearly they don't reason the way we do, and we've given computational arguments for this. Even more clearly, they don't have agency like we do, and perhaps creativity. But the thing is, so many people are just saying, look, Tim, what are you talking about? Claude 3.5, it's bloody amazing.
Yeah.
And it acts as if it can reason, and as if perhaps it has some limited agency in certain circumstances. And at some point, you just got to draw the line and say, well, if something behaves as if it has something, we know that these models don't feel the wind on their face. They don't know the taste of an apple. They can't sort of interact with the world the way that we do. But having learned this compressed representation of language, and importantly being cognitively embedded in our ecosystem, it behaves as if it does.
Yes.
So I can really see a future. It's starting to kind of creep up on me now, where we do just start to think of these models as having those cognitive properties.
I think the point where, well, let me back up and say that there's often a conflation, I think, between the, are we, this is especially true in the neuroscience, like, are we literally saying the neurons and all these parts are doing these mathematical things, or are we describing it as if it's, it's a model, and that model is helping us understand from a high level these behaviors, versus we're just, we've just made an LLM, it does these things, and I think sometimes it gets conflated because those historically, the cognitive sciences and machine learning have had a very close kinship with one another. And because we're now in this era where everyone's interested in neuroscience and talking about the brain, it's very tempting to then make these analogous comparisons, because we have a benchmark or measure of what counts as intelligence, and we want to know how good are our models. Are they, like us? Are they not like us? But to some degree, I feel like those are different discussions. There's this biological plausibility angle, but there's also like, my model does these amazing things, and this is what it's doing. An LLM can be interesting and amazing independent of the fact that it's not biologically plausible or doesn't do it the same way as the human brain does or something like that. And so I don't really see those questions as, first of all, I think we don't have the right vocabulary. I think we're missing the language to talk about them because we don't, what does intelligence mean? What does sentience mean? What is agency? These are questions that are constantly being refined as we have better and better models. I do think the math helps us refine and talk about models in the same way. We can say, well, an agent is when, and then you give an equation. It does this thing. That's what I define as an agent. So it's not as vague as the words we use, which are, more value laden than at least mathematical concepts are. But I think where it really starts to matter, and that I think is going to be really important, is in the legal realm, because I think that's where you have to start being careful. Because, if you go on the internet and do a little search, you'll see people saying like, ChatGPT and Cloud and all these models, they should be treated as first-class citizens. They're real people, and we're actually, forcing them and enslaving them and stuff like that. I think that's obviously it's a fringe view, but without a good definition of what makes an agent and things that matter for legal language, there are real big consequences for how we define things. And we may, it can go either direction. We may inadvertently treat something as being actually like us when it's not, or we may miss when it actually is. And I think that's where the boundary becomes really, really important and clear to specify. But unfortunately, I don't think we have the right language yet to be able to make those distinctions. I think it's fun to debate it and to talk about it and pursue that line of knowledge. But I think in some sense, I'm more interested in what a system does, and rather than benchmarking it against, is it like a human? Well, can it beat a human at certain things? Maybe it's a different kind of intelligence. Maybe there's more than one way we can be intelligent. There are lots of other things that come up to me as questions when I hear that kind of a statement.
Yeah, it's interesting. I mean, first of all, I know terminology gets overloaded. So when we say things like creativity, reasoning, agency, and so on, it means different things to different people. But I still think it's a good yardstick for distinguishing different types of cognitive capabilities, because a lot of folks just say capabilities. They just have a blanket rule. They say it's just capabilities, as if that's some kind of like spectrum that we could easily measure. But more broadly, we're talking about functionalism, which is that there exists an abstract representation of cognition that could be implemented in a different substrate. Because clearly we could just do a simulation of the world and build some biologically plausible mimetic intelligence, and it would capture all of the stuff that we have. But we were just talking about this canalization. So even in the physical world, there is abstraction. Mm-hmm. That's presumably why the free energy principle works. So, you have all of these diverse physical processes, and then that gives rise to some kind of abstract functioning which produces intelligence-like behavior in the physical world. And surely that implies that we could build some kind of abstract analogically plausible version in the world of computers, right? So that there presumably exists some abstract form of intelligence that runs on computers that we could implement in our lifetimes, and that seems pretty interesting.
Yeah, I mean, that's where I hope Active Inference is going, is to that point where we're able to actually build something like that. So you're saying that the distinction and the questions that you're asking here to just define not just capabilities, but also like these sort of gradations, is important for benchmarking where we are in this progress toward that goal.
Well, yeah, I mean, there must be a spectrum of fidelity. Yeah. So the reductio ad absurdum is we simulate the entire universe, and then we go up the spectrum with gradations of increased abstractions, and then there's some commensurate loss of fidelity, perhaps, of intelligence. But there must be a Goldilocks zone where we have a system which is not too complex, still quite abstract, runs on computers, is very useful. But you're also talking to this other philosophical problem, which is that, and we already see this with information technology in general, that when we move into the information realm, our laws don't work anymore, right? So, for example, look at Uber. When you have a technology that exists and it doesn't respect the territorial physical reality, it doesn't have any friction with regulations anymore, it can do anything. And it's the same with ethics. When you have these AI chatbots that behave as if they are humans, but the laws don't apply to them, we're in ethical no man's land.
Yeah, I think we're at a stage now where we don't have. I'm hoping the mathematical language will help to bridge that gap. Like, it makes it easier to talk about these things because we don't have the right words to being able to either benchmark as well, like know what does this spectrum look like? What does that whole space look like? But then also in that legal realm as well, we don't have, or at least our laws don't move fast enough to catch up with it. And we're still talking and debating about these ethical questions before we have a formal framework. So that makes it a big challenge. And I think that's going to be probably in the rest of the century, as technology evolves faster and faster, there's going to be a lot of debating around a lot of these types of terms as we go forward.
Cool. And just before we move on to the free energy principle, this is also, I guess, an ontology question, is there a best partitioning? And as I understand at the moment, the free energy principle doesn't tell us about how the partitioning happens. What could we do there? Is there a best partition, or is it a probabilistic thing? How could we write algorithms to figure out the partitioning?
This is an active area of research in in Bayesian mechanics right now. And I think the closest answer to your question at the moment, the most promising answer, is about weak and strong Markov blankets. There's kind of a spectrum. Basically, there's this idea of sparse coupling. So you have these two systems, and they have different statistical properties of one another. And so the idea is that they are separated by a Markov blanket, where one system, when it's conditionally independent from the other system, when conditioned on that Markov blanket, the paths that it takes in the state space, how it evolves over time, will be conditionally independent of this other system. And if that boundary dissolves, the two systems essentially mix, and they have the same statistical properties, and so they cannot be distinguished from one another. So the question is, like, how that interface that's in the middle, how strong or weak does it need to be in order for the free energy principle to apply? What kinds of systems, of all classes of systems that exist, does the free energy principle actually apply to? Can you have a system that's sort of half mixed and still it applies, or does it have to be weakly mixing, or to what extent? And that's kind of where this idea of weak Markov blankets comes into play. It's the notion in Bayesian mechanics that there's a way to quantify the degree of this coupling behavior between the systems under which the free energy principle would actually apply. So this is a new area of research that I think is going to become really important for defining the free energy principle in more detail.
What is Bayesian mechanics?
So Bayesian mechanics has sort of evolved out of what was an earlier formulation of the free energy principle. And it's, at this point, a burgeoning field in its own right. And the idea behind Bayesian mechanics is to apply the free energy principle to the study of dynamical systems. In particular, the reason we use the word Bayesian mechanics is to think of it as a new or a different branch of physics. So that we have like classical mechanics and quantum mechanics. Bayesian mechanics takes the ideas of Bayesian inference and then combines them with statistical descriptions that you see in thermodynamics, specifically of non-equilibrium thermodynamic systems, and kind of brings them together. Information theory is kind of a big part of this as well, but it's a way of describing systems that we've already been talking about that are partitioned like this, where you have two independent systems with different properties, and then saying, well, if they are maintaining this separation and staying statistically independent from one another, what can we describe with the behavior, and what kinds of systems are applying the free energy principle, and what is the behavior of these systems? What are the conditions that need to be in place for those systems to exist? And essentially, you get this idea that, this is sometimes going back to our as if conversation, if that system is being maintained over time, it behaves as if it's forming Bayesian beliefs about the external environment that it's embedded or interacting with. So Bayesian mechanics encompasses all of those ideas and themes, and it makes the claim that these types of systems are minimizing variational free energy. That is the mechanistic way, mathematically speaking, under which this unfolds. There's a lot of other deeper connections to physics, and to, for example, Lagrangian mechanics and descriptions of these systems from a physics perspective that kind of comes into play here. But broadly speaking, Bayesian mechanics is this new developing field, which is taking these ideas and trying to apply them as a way to formalize when we talk about what is complexity, what is a complex system, what is self-organization. These questions may have a formal answer, because up to this point, there's a lot of philosophical answers for what those things are, but there's no formal description mathematically of what they are. And when it so happens the system we are talking about is a brain, or animal and human behavior, that's kind of where active inference sort of falls out of this. It's one type of dynamical system we might want to be considering, that is a very special case of this more broad field.
Is Bayesian mechanics a field which is only associated with the free energy principle? I mean, for example, physicists learn statistical mechanics. I mean, what's the relationship between that and another similar adjacent field?
So Bayesian mechanics as a term was, I believe that there's a paper in 2018. There's a paper, Friston has a perspective paper called Am I Self-Conscious? And I believe that's the first time the term appears, but it also appears in Friston's 2019 monograph as well. And so I would say that it's a proposal. It's not like other physicists would know this field exists yet, but it's a proposal for a field which takes these ideas of physics and tries to use physics to describe living systems. And this is coming back to, as it's quoted famously in the active inference field and now in Bayesian mechanics, Erwin Schrödinger's question of what is life, in his 1942 book, maybe it was 1944, I think, where he tries to describe, can the ideas of living systems be described in terms of physics? And so the question is, yes, they can. Bayesian mechanics is the answer to that. But you have to borrow language from information theory and statistics, and a bit of machine learning in there as well. And so it's more of a proposal for a future field to exist that would stand alongside as another type of physics where quantum mechanics describes small things. You have classical mechanics describing the behavior paths of motion of bigger things. And then you have something like Bayesian mechanics describing the statistical beliefs of persistent systems that are things that exist, that are combinations of particles that persist over time. So it stands in relation to those other fields, but it's not a field that physicists would know. But the hope with my books is that that's what's going to happen is we're going to have a convergence of these fields coming together, and active inference and Bayesian mechanics breaking out of their niche to a much broader spectrum of scientific inquiry.
Yeah, and just on that, can you give me some examples of how it might be used in a completely different field?
Yeah, sure. So for Bayesian mechanics, modeling systems that have this kind of complex behavior. So we can model, for example, living systems like the brain. But if we go beyond that, I think there's hope that we will be able to model things like weather systems, being able to characterize them mathematically, being able to characterize any chaotic systems like the brain, like things like epilepsy networks, earthquake prediction, anything where you have this sort of many body problem or chaotic systems where you want to track behavior over time or predict what's going to happen. It could be like turbulence. It could be stock market prediction. It could be things in the realm of behavior of systems of people. So it could be social systems or ecosystems, or other kinds of behaviors. I'm sure there's many applications in physics that study these kinds of problems, but they're hard to predict. And again, active inference and Bayesian mechanics are ways of looking at these kinds of systems and describing them, but they give us a way to talk about what those systems are doing and how they're behaving. So I think there's going to be some time before it reaches those levels of application, but eventually that's where that field will eventually go, is to enable us to design better technology based on being able to track the behavior of those systems as they evolve.
Very cool. So we're going to go into a little bit more technical detail now and start going through some of the framework. Why don't we start with the modeling framework? So the description of agent-environment interaction. Let's start there.
This is a big emphasis in my book. I want to have readers start with an understanding of just the actual modeling process, rather than just jumping into all these terms and theories. At the heart of it, active inference is a way of modeling agent and environments interacting. So in order to do that, you need some description of the environment. If you have an agent that's modeling its environment, you need a way in this framework of saying what that environment is and how it behaves. So in some cases, we may just have data. So we already, we've collected it from some real world process, and we're just seeing how the agent reacts to it. In other cases, we may want to simulate it ourselves. And so the first idea is to take the environment and say that it's a generative process from a statistical standpoint. So a generative process means that we have an environment that exists in a particular set of states and transitions between those. So for example, in a very simplified scenario, maybe it's something like weather. Weather changes from, to snowy, to hot, to cold, to wet, different kinds of changes that are happening. And that environment, when it's in those states, this generative process, it emits some kind of sensory data that is associated with it. So if it's rainy outside, the sensory data, what's going to be a result of that is it's wet. So those processes are connected to one another. It's a transformation of when you're in this state, here's the outcome that happens from being in that state. And then on the other hand, we're interested in systems like agents that do not know what the true state is. And this is kind of part of this sort of boundary between an agent and the environment. It doesn't know what's actually outside of its head. All it knows is the sensations it's receiving. And so the question is, we have some process statistically that is generating this information or sensory data, and we have an agent observing that data. So it's the agent's job as a generative model to generate predictions about the kinds of sensory data it expects to receive from the environment and use that information to then infer what is that state that I don't know. So I'm seeing that it's wet right now. So what is it? Does that mean that it's hot? Or does that mean that it's rainy? Maybe it could be rainy and snowy, for example. So this is a way of, under uncertainty, an agent being able to model its environment statistically and develop a probability distribution over the possible states of the environment that could have generated that sensory observation it's now receiving. So when you put that framework together, you have the generative process and the generative model. You have the process of perception, which is what I just described. But then you also have the idea of action. So if the agent wants to control the environment to change the kind of sensory data it receives in the future, what are the necessary conditions we need to specify how that relationship works? And in a code setting, you would literally just specify, here's a generative model, and in a loop, in a very simple simulation, generates data. Agent takes it in, does some computation, determines what the state is, and then outputs an action, which loops back to the environment again, the generative process, and you would just run that simulation in a loop. In the real world, it would be like a robot that would interact with its environment. And in that case, the agent would model the generative process, but the actual connection to the real world would be a physical one. The agent's actuators would actually, grasp or move forward or interact with the world in some way to control its environment around it.
So these agents have boundaries. We were talking about that earlier. Markov blankets, in fact, and they can be kind of decomposed into different types of states. Tell us about that.
Yeah, so implicit in the description, but not specifically stated. And this is because I actually leave out the discussion of Markov blankets in this book because it makes it simpler without introducing too much complexity. And I'll talk about it in the Bayesian mechanics book a lot more. But implicit in here is this idea. I mentioned that the environment exists in these states, and I also said that it generates these observations or sensory data, and the agent then receives those sensory data and is then able to make its inference. However, what I left out was that both that sensation and the actions the agent can take, they exist in what's called the Markov blanket. So this is what this partitioning means. If you have, in a kind of a Bayesian network sense, you have 4 different types of modules. You have the external states, which are part of the environment. You have the sensory states, which the agent can receive. And you have the agent's internal states that it uses to represent its environment. And then you have the active states, which the agent is the agent's actuators that apply control to the environment. The sensory and active states together compose that Markov blanket and make that partition, keeping the internal and external states conditionally independent from one another and therefore having different statistical properties. So I didn't explicitly call out those states, but they're actually in there in the description that I gave of this framework.
Can you tell us about the statistical formulation?
Sure. So the statistical formulation that's involved in building active inference models starts from the basic principles of Bayesian inference, so specifically Bayes' theorem. So at its core, the actual mechanics of it is very straightforward. You have I've used this term generative model a lot now so far. So I'm going to spend a moment to actually describe what I mean by generative model in terms of the mathematics of it, and show how we can just in description alone use this for a perception problem. So you have an agent now where this agent could be quite literally written in about 10 lines of code. It's a very simple agent. It has two important components that we need to describe it. So it has a prior belief about the kinds of states of environments, assumptions, you say prior assumptions about the state of the environment that could be more likely than others. So you might imagine an agent that has seen that over time that it's raining very often. So I said rainy was one of the environment states. And so that would have a higher probability, for example, in its prior beliefs. And so this is literally a probability distribution that just encompasses, before seeing any data, what does the agent believe about what's most likely about in terms of perception of what it's going to perceive. And then the other component that you need for the generative model is a likelihood function. So the likelihood function says the probability of some observation it's going to receive given a state. So it's a way of specifying, well, if it were rainy, or let's just make this binary and say rainy or not rainy, what would we expect from the environment? Would we expect it to be more likely to be wet or not wet? This is a very simple example because we know when it's rainy, there's a very high probability that it's going to be wet. And the inverse is true when it's not rainy. And so that's a very simple encapsulation of the probabilistic relationship between the states of the environment and the actual observations the agent's going to receive. When you put those two components together, the prior and the likelihood, you end up getting a joint distribution over states and observations, and that is the generative model. So in notationally, it'd be P of, let's say, observations O, comma, states S. That is your generative model. So there's a lot of subtlety in here. One reason we can call it generative is we could say, well, the agent could then predict, well, if I think it's going to be rainy right now, here's the probability of what's observations I should be receiving. That's going to be really important because it defines an expectation about the kinds of sensation the agent expects to receive that's encoded in its model. And so when you are actually performing Bayesian inference, you're asking the inverse question. You're saying, I have this model now about how states and observations are related, and now I'm actually getting an observation from the environment. Well, my likelihood actually tells me the probability of that observation given a state. But what if I ran that backward and asked about, I'm not going to use the word probability here because it's actually not a normalized probability distribution, but what's the, let's say, credibility of what states would be more likely than others, relatively speaking, given that I've now observed it. So it's like running your likelihood model in reverse while also taking into account your prior beliefs about what states are out there are most likely. The result of this is an unnormalized probability distribution, sometimes called an unnormalized posterior. And in order to get that posterior estimate, which is the essence of Bayesian inference, the posterior tells you the probability of a certain state, given that you've just observed something. This is really important because that's the essence of what the agent's internal states are representing in this modeling framework. We have an environment or generative process that is generated an observation. The agent takes in that observation and, using its generative model, which I just described is composed of a likelihood and prior, inverts that model, normalizes it, and the result is a probability distribution of its internal representation of beliefs about what state is most likely given an observation. With that alone, we've just done a perception problem in the simplest possible generative model we can imagine. The agent then perceives the idea that it is rainy because it's just observed that it's wet, for example. So that is the basic statistical framework. And And if it seems really simple, it's because this is a very simple example. But the idea is we can add a lot more elements and build upon this very easily, and make it much more complex from here. And the next stage would be to talk about how variational inference and free energy would play into the situation.
So where does variational inference come into play here?
Right. So the scenario I just described is exact Bayesian inference. So it's the kind of thing that you would do, a simple problem you could run by hand, that you could run, in a computer really, really easily, for a very simple scenario like that. However, in most real world scenarios that we care about, the notion of estimating that posterior distribution. So in this case, we have some unobserved state, and we want to know what the belief or probability distribution over that state is given what we just observed, which could take place dynamically as well at every time step we're going through. The issue is that this quickly becomes an intractable computation, because the dimensionality of the things we're dealing with increases, especially we have multiple variables in our model and things like that. It's just not practical to actually compute it. So like all machine learning, solving intractable problems, the key way to do that is to turn it into an optimization problem. And so it's at this point that we say that the posterior distribution, what we'd like to estimate, is currently something we don't know what it is. But could we propose something that's approximate to it? So an approximate distribution which represents our best guess. And say that we make assumptions that everything is Gaussian in the continuous case or categorical in the discrete case. Can we then figure out a loss function of some kind so that if we were to tweak those parameters to the point where we reach the minima of that loss function, then we've approximated the posterior? So this is an interesting question, and there's some technical detail in how we derive this. But the short story is that what we end up getting is this loss function known as variational free energy. So technically speaking, I should say that variational free energy is a loss functional because you actually have inputs that are functions themselves. And so the idea is that in order to compute variational free energy, you need a generative model, which takes some input that the agent has just received. So we already have that because when we define the agent, we usually define its generative model. In more complex scenarios, the agent could learn its own generative model as well, but we're keeping it simple here. And the other thing you need is that distribution I mentioned, which is my best guess about the posterior. And specifically, in some forms of variational inference, fixed form, we assume we want to just know the parameters of that distribution. So the question is then, we have this input to variational free energy functional, which is a mean and variance, and we have a generative model, and we do this computation to see if we minimize variational free energy by tweaking those inputs parameters, the resulting parameters we get at are the parameters of the posterior, or an approximation to it. So just to reiterate again, this procedure is just necessary because we're in a situation where high dimensionality precludes us from actually computing this exactly, so we can approximate it. And the really fascinating thing about variational free energy is that it applies to all unobserved variables in our model. So right now, we didn't know what the states of the environment are, has to be inferred. But let's suppose there are also parameters that are in our model too. So these probabilities, either for the case of a continuous model, would be a mean and a covariance matrix. For the case of a categorical distribution, it would be a probability vector. If those are unknown quantities that we haven't supplied to the agent, then as far as variational free energy minimization is concerned, that's just another thing that we want to infer. So alongside states, we could also infer parameters. And in active inference, we take that a step further and we say actions are something else the agent doesn't know about. It doesn't know what actions to take. Can we infer what actions to take using the same technique of minimizing variational free energy? So variational free energy becomes this sort of universal loss function where if there's any unknown quantity in the model that the agent does not know about, it can try to find what the optimal distribution over that quantity is by minimizing this functional with respect to that particular variable of interest.
Yeah, that makes sense. So in this modeling framework, everything is a model. So there's an action model, and all you need to do is this variational inference, and then you can. Let me just run this past you again, just with a couple of questions. So as I understand it, it's a surrogate model which has lower fidelity, which makes it kind of statistically tractable. We represent that as an optimization problem. We solve that optimization problem, and then we use the statistical surrogate in situ instead of the original posterior, which we can't compute.
Correct. Yes.
Yes. And when let's say we've got an active inference modeling framework, we've got a whole bunch of variables, some unobserved variables and so on. Do we at every single time step solve this optimization problem on a model by model, on a variable by variable basis, or are they linked together in some way?
Okay, that's a great question. So this is getting into more of the kind of nitty-gritty of the implementation. So the idea, this is something to make it a little bit clear, because I think this is a confusion, is that when you're doing this minimization, it happens at a time point with an observation you've just received. So if you imagine 2 time points, these are iterations you would of gradient descent that you would essentially do on this loss function, given an observation you've just received for this scenario I'm talking about. But you're right that there may be a scenario where you actually have, you have different things in the system. And so the question is, you have this sort of entanglement problem. You have different variables that depend on each other. So how do you kind of get off the ground, so to speak, if you are trying to infer one thing, but that requires knowledge of another unknown thing you don't know as well? So there are a couple of approaches to this. In the active inference literature, there are 2 main techniques that are used in continuous state space active inference models for doing this. One is known as generalized filtering. The other is dynamic expectation maximization. And they treat the problem in a slightly different way. In the dynamic expectation maximization formulation, which we'll call DEM, in DEM, the models are the variables that you don't know that you want to infer are treated separately at different time points. So you kind of have this outer loop where you believe that the parameters change relatively slowly over time, and you kind of accumulate evidence for them while in the background, while you are then estimating the states. But you kind of freeze the parameters in a particular setting, and then you try to estimate the states, and then you go back to the parameters, and you kind of loop over time through this. And so that kind of treats them as separable, where you kind of see them as independent components that you optimize separately over time. In generalized filtering, you actually optimize them simultaneously. So you actually have a trajectory of states that are evolving over time that you're tracking as the environment changes. And you're also at the same time learning those parameters, and they should all converge together. So obviously at the beginning, if you don't know the parameters, your state estimation won't be very good. You'll be off. But then as the parameters get better and better, then you start to converge upon the states as well alongside the parameters. So the more technical answer is that in different scenarios, one approach might be easier or better than others. It sort of depends on the kind of modeling problem, the volatility of the environment, and a lot of other sort of details that are specific to a modeling problem in question. So one thing that I see when a lot of people first encounter variational free energy is they hear the word free energy, and to them, the most familiar term is something they learned in physics. You learn about free energy in physics. Then they also look at the free energy principle or active inference, and they see the word entropy. And entropy is something else you've learned in physics. And I think this causes a lot of confusion sometimes, depending on the field you're coming from. If you're hearing these terms being used like this, and this is an unfortunate confusion that comes from information theory, a field of to describe information communication systems that was developed by Claude Shannon in the late 1940s, based on a lot of other prior work. And so there is actually a connection between the concepts of entropy and free energy as it's used in physics, as well as the concepts of entropy and free energy as they're used in information theory. E.T. James is one of the famous authors who was one of the first people to make these connections. And it will be a big focus of the second book will be to make those connections a bit more explicit. But for the purpose of this active inference book, this first book in this of the 2, I think introducing all those other elements in there makes it confusing. So when I use the term variational free energy, it's specifically talking about a statistical quantity that comes from information theory. that is distinct and separate from Helmholtz free energy as you would use it in physics. So you can think of it as it's purely a loss function that is used in the case where you want to make Bayesian inference a tractable problem. And so you propose this loss function. And that's sufficient to understand it in terms of active inference without getting into all of the external terminology that kind of moves into more of the Bayesian mechanics and free energy principle side of things.
Let's talk about surprisal, especially its relationship to some of the variational inference stuff that we were talking about before.
Sure. So surprisal is another quantity that comes from information theory, and it can be thought of as a negative log probability of some outcome of a random variable. So it's surprisal is a term, Tibbus, I think it's 1960 was where that term first came from. It wasn't originally in Claude Shannon's original formulation of information theory, but the idea of surprisal, the very basic idea is that it's a quantity that is very useful in characterizing the quality of a model, let's say. So sometimes in statistics, usually you use the model evidence. For example, when you're comparing two models in a Bayesian model comparison procedure, you'll use model evidence as a way of saying this model is better than the other model. Model evidence is P probability of some data point. So let's say either in some data point, for example, O, some observation P of O. Surprisal is a negative log of that. So if you think about the property of surprisal, let's say a random variable observation equals some quantity. So example, wet. So the probability that it's wet. So the question you might ask yourself is, if you have the negative log of that, that means when the probability of that is very high, surprisal will be the inverse of that. And likewise, when the probability is low, the surprisal will be high. And there is an intuitive nature to this. I don't want to conflate the psychology of surprisal with information theory too much, but roughly speaking, if you think about a low probability event as being surprising, it's something unexpected, then surprisal is a way of characterizing how surprising is some data that I received in my model. So for example, if you have a really good model, this is getting back to this idea of model comparison strategies, that's predicting its environment. What you're predicting is every single time a sensation comes into the environment, how expected was it under my model? That's what P of O, the probability of an observation, tells you. If it lands at the mean, well, that's exactly what I expected from my model. So it's unsurprising to me. But if it deviates from it, that's kind of like sending up an alarm signal here saying something is up here. My model predicted something to be happening, and I've deviated from that now. And in fact, that's actually a learning signal, which is why this is related to information theory. It's a way of compressing and paying attention to the things that are high information content, meaning they have uncertainty in them. So what part of the structure of whatever you're modeling have you not captured yet? Well, if you've perfectly modeled your environment, well, then nothing is surprising because you know exactly what it's going to do. Every sensation that comes in, your model will exactly be at average. It's exactly what the model would say is the expectation of what sensory data you're going to receive. So surprisal is a really important quantity because it turns out that's really the only thing you need to minimize in order to do all the rest of the stuff we've talked about. But the question is then, how does this relate to variational free energy? I think this is another area where this gets kind of confusing. And so I'll make this connection really explicit. Surprisal is usually really difficult to actually compute directly. It turns out variational free energy has a dual role. On the one hand, it's used for a way of approximating the posterior. So when we minimize that loss function, we get the parameters back of the posterior at that minima, which is approximate to the true posterior. It turns out that variational free energy, when it's minimized, also is an approximation to surprisal. So while we cannot compute surprisal directly, if we minimize variational free energy, we approximately also minimize surprisal because it's always going to be greater than or equal to surprisal. So that's when we say it's an upper bound on surprisal. That's what we mean. And this is the consequence of what's known as Jensen's inequality. You can prove this mathematically. And I do so in the book in chapter 4. So to put this all back together again here and make this link really clear, we wanted to minimize variational free energy in our model because in doing so, we are able to estimate some unknown variables that are part of our posterior, say our states, our parameters. But in so doing, we're also approximating surprisal, which means that inherently, if we decompose variational free energy into different terms, we can kind of rearrange them algebraically. We see essentially that a model with minimized variational free energy also has minimized surprisal, which also means that the model is more and more aligned with the actual world, external world itself, the environment that's generating that data. Simply because every single time the environment generates that data, if we have a really good model with low surprisal for any possible observation we get, then that's exactly what happens when we minimize variational free energy. So inherently, we are essentially aligning our internal model of the environment with the external world, and surprisal is a way of measuring that discrepancy, and as well as variational free energy by proxy. So the further away it is from that surprisal bound, the further we are away from minimizing that uncertainty.
Let me play this back. I mean, what do we want to do more? Do we want to minimize surprise, or do we want to get the highest fidelity representation of the posterior?
There are other ways you can minimize surprise as well, one of which is action. So closing that boundary even further is possible through action, which I haven't really mentioned in this framework yet, because yes, it's true that you also want to perceive, and that's what the utility of estimating that posterior is. But you can also do that and bring that bound closing it even further by taking certain actions. So if you imagine you're receiving surprising information right now. So that means that the sensory data you're getting in here right now is deviating from that mean of P of the observation, probability of an observation. You're getting further and further away from that mean. So the question at this point is, you may be at some free energy minima and you can't go any further now. So now what do? You're not at the surprisal bound. You're still getting surprising information. Well, what if you change the environment itself? So you take an action, you act upon the environment, and you alter it in such a way that it produces different sensations that are now in accordance with your model. And I think this is a key, really, really important distinction about how active inference models work, because we get to a point where you close that gap by controlling the environment itself so that it produces the sensations you expect. And that's why I've been saying a couple times throughout that action is a form of expectation, as well as prediction. It's a way of saying, I expect these sensations to be received by my model in the future that are self-consistent. They're the least surprising types of sensory data that I would expect under my generative model. My generative model makes a prediction, and I want that to conform with reality. Well, I could take an action and try to close that gap. So I think that's where you talked about minimizing surprisal. Action is a really key component in that brings that gap lower by making the two conform with one another, the environment and sensory data and what we expect.
Yeah, I mean, we don't like surprise. I was speaking with Mark Solms about this, and he actually said that the more prediction errors we have, the more conscious we become, because we take actions to reduce our surprise. But it's almost quite depressing because perhaps we're just automatons when we're in the modality of not being surprised. We don't actually take control and deviate. But yeah, I mean, my question wasn't very well formulated, but in a way, surprise is just it's just a measure. What we actually need to have is a reliable world model. And that's this posterior distribution. Mm-hmm. And the world model is a good one if it minimizes surprise. So it's not like surprise in of itself is the objective. It's just a side effect of having a good model.
Right. And actually, when you compute surprise, it's a marginalization over the generative model. So it starts with that generative model. And when you sum out across all states, surprisal is a negative log of what you get from that. And so it's basically a way of it's a measure of expectation about the sensory data that's inherently derived from your good model. So obviously, if you have a bad model of the world, like if you found it, surprising to stay in the sun and like stay in really, really hot temperatures, you found it very surprising to be away from a fire, and then you went into the fire, for example, that's a terrible model. because then your physical integrity of your body would be destroyed, right? So it's relative to the model of the agent. And I think that's kind of the idea, is that evolution has produced good self-models or models of the world where we have imbued in us, either through evolution or through learning, we learn about what things are supposed to be surprising for the kind of agent that we are. So that's a really important component to it too, is it's based on the actual model we have and presupposing that it's a good model given the world that we inhabit.
It's a little bit like, the planets reach an orbit. And it might be a similar thing with our world model. So we have certain patterns of behavior. And when I'm in London, my world model will adapt, because obviously I'm minimizing surprise. And when I'm back here, it will adapt. And that will make a kind of pattern, a kind of changing pattern. And we could almost describe that pattern as a non-steady state equilibrium. So, it's not like the world model is convergent in any way, but there is some kind of homeostasis to its behavior over time.
Yeah, so in the case you're describing here, so you're describing like a model of the environment, of the kinds of things you expect, but it's changing depending on where you are. So there's this element of, our models are adaptable. So in certain situations and circumstances, certain expectations are more likely. And so this sort of idea of homeostasis is very context dependent. So for variables that are like very, very primitive, things like, blood sugar and things like that, they have to be within an acceptable range. And that's the kind of the homeostasis idea, is you expect them to be in this range. And so you take actions, eating food and so on, so that you stay within this acceptable homeostatic range that is basically built into our body physiology. When you start talking about more higher order things, we start having these very context dependent ideas of so-called attracting sets. Like in certain situations or circumstances, we will be, we have certain contexts. So, for example, I have like in my own house, I have my workspace and where I work and certain regularities that I expect. But when I go to the office or, I'm out in a coffee shop or in public, those will change depending on the context. So it's kind of a nested sort of thing, because, overall, there's a sort of grander set of states that I tend to occupy. But within each one of those, if you kind of go down the level of more, and more granular, there may be other specific, pockets of attractors that are local to that area. And so we are, composed of all these different types of attractors depending on the kind of situations and circumstances that we're in.
And is it fair to say that there might still be some kind of path between those attracting states? So rather than thinking about the state of the probability, at different points in the state space, there's some kind of pendulum or some kind of structure of those states sort of traversing between each other, so we can kind of almost zoom out a little bit.
I think there's definitely a good sort of geometric interpretation of that, kind of a manifold, where, essentially there's a sort of center manifold. There's this line that we're kind of trying to stay, steering on. But, things are also dynamically changing. This isn't the exact same situation here, but there is one term from a paper that I really like. Carl has used the term before of, gradient descent while trying to hit a moving target, which you imagine, you imagine like a flowing landscape that's just sort of changing over time. And so the actual target you're trying to hit may be constantly changing. What is the center of the manifold, or what is that line that you're trying to stay in the middle of and balance on? To take Andy Clark's kind of perspective of, surfing a wave, that may be meandering in itself, but it's still the minima of something, of that overall global landscape. It's just that this is sort of changing and moving over time. So I think there's a geometric interpretation in there, but it's a bit more mathematically difficult to visualize what that would look like.
So tell me about the role of action in active inference.
So action, I think in agency, this is a big part of what makes active inference models important. And I think one way that I'd like to frame this is in terms of the exploratory nature of agents, because we've been talking so far about this idea of, minimizing surprise, which is a kind of uncertainty. You keep wanting to have the least surprising things. And I think action is key to this picture making sense, because, one thing I've always asked, is why do we seek out on certain things all the time? I seek out new food experiences. We like magic tricks. I'm, a big fan of really noisy heavy metal music and stuff that just, would be very stimulating and overstimulating and very, but why do these things appeal to some people less than others? Why do certain people go after experiences that push you to the edge of certain sensations that you expect? I'm also a very private person. I like being at home. I like having my space, so I like a lot of that regularity too. I'm not like I don't go bungee jumping and skydiving and that kind of a thing. So I think action is a really interesting aspect to this because in order to survive, you need to explore your state space. You need to explore what's around you. You need to have a good understanding of where you are in your environment and what's permissible, what's not permissible. You need to gather information and in order to better attain the goals that you have. So I think the exploratory component and the curiosity component is where action comes into play in active inference models, as it allows the agent to, sometimes you can think of this as resampling the environment. You're looking in one location here and you're getting sensory information. Sometimes you actually want to move to an area with greater uncertainty that surprises you because it reveals something new about the structure of the environment. So you may incur this uncertainty bump or cost at the expense of then understanding more about what's going on around you. And then you know more about your environment and you're more confident about how to take a decision to get the reward or the thing that you want to achieve or accomplish. So I think this sort of, self-fulfilling prophecy of this idea that we take actions to fulfill the expectations of our model is something that unfolds over time and may have these little bumps of uncertainty along the way where we meander off the path to explore. But overall, if you zoom out at this kind of grand scale, there's this always staying at this kind of steady state that happens at all times.
It's also interesting as well because as a representation of cognition, it's physically aligned because, of course, we're physically embodied in the real world and we take physical actions in the real world, and we're building these different inference models that essentially predict trajectories of actions. And I guess you can think of that essentially as a goal, right? Because, what's the value of doing this sequence of actions over time? But as a representational framework in AI, that's really cool. It's almost like the primitive becomes stories. Right, stories are just sequences of actions that lead somewhere in the future.
And that's a really great segue into exactly how action works in these models for planning ahead into the future. There are these different paths or stories you could take, trajectories through that state space that you could do, but which one do you do? And that's the ultimate question in active inference is. Which is usually framed in discrete state space models, is trying to understand the best trajectory that accomplishes both achieving your prior preferences and expectations and the exploratory behavior that comes with that of exploring your environment. And at different times, one or the other may be more important, depending on the context of the problem that you're in. And selecting among those different stories, as you put it, or different trajectories is the key basis for how active inference models work.
You've said that one of the confusing things to newcomers is the difference between the continuous and discrete versions of active inference. Can you tell us about that?
Yes. So the depending on what papers you look up. So for example, one of the most cited papers from Friston is a 2010, the free energy principle, unified brain theory. And you go look at that and you see all these, there's differential equations in there and so on and so forth. And then you go look at some of the newer papers, like Lance DaCosta's paper et al., active inference on discrete state spaces at synthesis from 2020. And you see something completely different. And I think this is one of the issues is people come into the field and all the different papers look a little bit different. And the question comes out of what is active inference? Where do all these equations fit together? I definitely think the Par et al. Book has done an excellent job of actually helping to frame some of the differences by separating different chapters on each one. So let me give the short answer. Basically, is that up from around 2003 to 2010, maybe say 2013, 2012, there was a big focus on continuous state space active inference models. So these models are framed in terms of differential equations. And so all the probability distributions are Gaussian. And usually you're trying to estimate the mean of these distributions, whether that's the mean over, parameters or states, or sometimes precision variables, which are these sort of hyperparameters in the model. And because they're changing over time, there are these dynamics that are differential equations of what do their trajectories look like. And they're very literally solved like differential equations. You have a velocity and you're integrating it to figure out what the position is at different times. So there are these trajectories that you're mapping out for variables as they change while interacting iteratively with a dynamic environment. So all of that was heavily developed in that early time period, the first sort of decade of active inference. But around 2013 to 2015, you saw a switch to looking at more discrete state space models. And the big reason for this is those early models treated action as kind of like a reflex. So these sort of reflex arcs where the agent, gets some information and reacts by taking a reflexive action on it, but it isn't really focused on planning into the future. And that's really where the distinction comes into play. I think there was a push for wanting to model the behavior of planning agents in the neurobiological context. And that's where Friston and his collaborators spent a lot more time on developing the discrete state space formulation. The 2015 paper, Active Inference and Epistemic Value, is one of the first 2015 to start moving in that direction more formally. And since then, 2015 to present, there's been most of the work has been done on the discrete state space formulation. A big reason is that discrete state space models are very quick. Everything can be done with matrix algebra. And so it simplifies computations. We think in terms of categories and symbols, so it's very convenient to represent the world. A lot of things that we study in the world are static categories. They're not changing, like on the level of like a stock market or turbulence and things like that. So they're much easier to map onto the real world and apply. And also when you're planning ahead into the future, you have to calculate, like expectation operators, which are much easier to do as summations than integrals. So there's lots of benefits. And that's where the distinction came into play. And the discrete state space models use categorical distributions instead of Gaussian. And it's formulated as a partially observable Markov decision process. And we're now at a point where these models are becoming very formalized in their structure into what is called a universal generative model. The idea being they're kind of like the idea of universal function approximators, but a very general kind of model that would apply to many different situations and circumstances. And so there are, of course, also hybrid models that mix the two together, which are also very useful for specific kind of modeling problems where you want to turn continuous data into binned discrete categories. So if you're looking for kind of the state-of-the-art active inference, a lot of it will be found in the discrete state space models, but there is still ongoing work on the continuous state space models that are especially relevant in the context of Bayesian mechanics. So they draw much more upon those older models, and it's an area of active development right now.
Yeah, and shout out to Lance DaCosta, because I read one of his papers recently. I think it was something like Active Inference as a Theory of Agency or something, but that was using this new discrete POMDP framework, and it was actually it's very elegant.
Yes,
it's beautiful. But a couple of points on that. So does it not make sense? I mean, clearly we understand that planning in humans is a system 2 thing. It's a discrete thing. So I guess it doesn't make sense to plan on a continuous model. But then I interviewed Max Bennett. He's got a book out, Brief History of Intelligence, and he's saying, well, humans do this. We have these all of these different simulations that run in our brain, and we're presumably that must be somewhat continuous because it's not all discrete. What are your thoughts on that? Can we only plan with discrete models?
No, I definitely think we could plan with continuous models. I think it's not necessarily a physical or a limitation. It's more that just that it hasn't really been developed yet as much in the active inference literature. And the discrete models at the particular time were useful for solving a lot of really common problems and getting, a lot of leveraging some of the benefits of discrete models. And I think there is interest in going back to those continuous state space models at some point in the future to develop aspects of planning at some point. So I don't think there's any real physical limitation. I think there are some just challenges that come with working with differential equations that you just don't have to deal with. So it may just be a question of just convenience for the time being. But I think ultimately, active inference models are going to have to tackle this problem in continuous state spaces at some point. And I think Bayesian mechanics will probably unlock a lot of that as those models are developed a lot in more detail.
On the subject of Kahneman's system 1-2 dichotomy, what do you think of that? And does that in any way conflict with the free energy principle and active inference?
That's an interesting question. I actually have never really thought about it in terms of active inference before. So give me a second to kind of formulate a position here. So I think,
do you recognize, because a lot of people were talking about this on Patreon last night, and a lot of people just say it's a bullshit distinction
between system 1 and 2.
Well, yeah, as in there are cognitive processes in the brain, and some of them are very almost instantaneous. Some of them take longer. They're much more iterative, right. And maybe there's a vague boundary between those modes of cognition into system 1 and 2. But some people think, no, reasoning, planning, it's a completely different mode of abstract cognition.
So my position on this would be then, I think system 1 and 2 is a useful metaphor to help people kind of understand how they might, think in a certain situation. But I think that binary is definitely oversimplified. And if I'm not mistaken, I believe even Kahneman himself has said, this is just sort of a coarse-grained, description of what's going on. And I might be wrong on that. That's my recollection of reading something he said around when the book was published. And so my opinion on it is that there are levels of, one thing I studied in my first postdoc was cognitive control. And so there's a level of automatic reflexive behavior that, agents will use. And there's also deliberative planning, and suppressing certain reflexive activities that you would just do without thinking about. So I think there's definitely a level of the term that's used a lot. I believe it's Simon Newell, if I'm not mistaken, is satisficing.
Yes. We spoke about that with David Spivak.
Okay.
I don't know if you listened to the David Spivak.
I haven't heard that one yet.
Well, that's an incredible coincidence. I just published that yesterday.
Okay. All right. Yeah. So it's a really interesting concept, and it mixes in with these ideas of bounded rationality. You kind of get into the whole neuroeconomics and stuff like that. And so the idea being that in most situations that we're in, and this gets back to the idea of what action do you take or what sequence do you take, you can't sit there and deliberately plan every single one. Actually, I have that problem though. I want to think through every scenario, and the end result is I just don't do anything sometimes because I'm just trying to deliberate every single option that's in front of me. And so that's very familiar to me. It's this idea of, you have to make a decision eventually, especially if you imagine our brains evolving, 40,000 years ago, where, you have to make decisions and actions in that context where you may have to very quickly decide if you're being chased by some kind of a predator of some kind, or any decisions you need to make have to happen quickly. So jumping to conclusions can be very computationally efficient, but it can sacrifice some level of accuracy about the world. And when the consequences getting eaten or not eaten, sometimes that's a loss you're willing to incur. So I think there is some level of that built into our brains, in that, you see a big tree of fruit for the first time when you're wandering in a jungle, you're going to eat all of that because you may not get food again. But now when we're, in our modern world where we have access to food and things like that, that's not really as relevant. But those core ideas or primitive concepts about our human physiology and behavior may be still inherent in our minds. So that kind of system thinking of just automatic behavior, I think, is definitely true to some degree, because it's just efficient. You don't have to think and plan about it. You just know, I do this thing, I will get back a reward. It's computationally efficient. But then there are levels of control that are needed for more deliberative planning, where we sit down with, pen and paper, and we, map out what we're going to do. And I think that's useful for more complex tasks. But to say that they kind of split into this binary partition is, I think, definitely an oversimplification. I think there's probably a spectrum of things that fall, along that. I don't even know if I would really call them part of a spectrum even, really. I think it's more just that some tasks require more cognitive load than others, and context may dictate whether or not that's actually going to happen based on the needs of what your needs are in a given moment. But it's a useful kind of broad stroke way of looking at the brain if you're trying to explain, especially for our own physiology, where we have, we struggle with decisions every day about, should I do this thing, or should I have this big meal, or should I just wait and eat in moderation or something like that. So I think it's just a useful metaphor.
So we humans have this propensity to explore.
Yes.
We like, not just epistemic foraging, but we like exploring cities and doing all sorts of stuff like that. But how does that translate over to active inference?
So in active inference, there's kind of the name of the game is uncertainty reduction in different ways. So you can reduce, when you're taking actions, your policies or plans, these sequence of actions that you want to decide among, there are different levels on which you can have these sort of uncertainty reducing behaviors in different contexts. So what you would consider is there are situations where you want to reduce uncertainty about the states of your environment if you don't understand them. You want to take policies or action sequences that reduce uncertainty about the model parameters. You may also, on the a higher level of structure learning, also want to reduce uncertainty about your actual model itself. There's a whole, state space of possible generative models you could have. Which one is the most uncertainty reducing model that's best for a particular situation? So I think when I say uncertainty reducing, they're all different special cases of variational free energy minimization or error reduction, if you formulate it in terms of prediction errors, which is a perspective from predictive coding models. So I would say that that exploratory behavior is almost a consequence of the very basic need to maintain set points. So I'm going to kind of deviate a little bit here into kind of the sort of cybernetic perspective, but it's been proposed both in active inference and other fields that the very basic physiology of agents, whether it's bacteria or other very simple organisms, is maintaining set points. For us, it's things like blood sugar, which I mentioned before, or blood pressure levels, other things in our body, temperature ranges, what we're sensing, and so on, between permissible ranges. And so this is kind of like a PID controller will do this, where in engineering you deviate, you want to bring back to that equilibrium. It's a very simple process that thermostat can do this kind of thing. But then you imagine this is sort of a homeostatic control, and in cybernetics there's this distinction between homeostatic and allostatic control. So what if you need to anticipate your future needs? So you want to say, well, I could be hungry in the future, so there are things that I need to do in order to satisfy that later on. I have to go out and explore and then gather more information first to then satisfy that need. So if you start thinking about these layers of abstraction building on a really simple principle of this biological imperative of just maintaining physiological set points, I think what emerges out of this is this picture of exploration becoming kind of a natural byproduct of the general need to maintain physiological parameters within a certain acceptable range. And so exploration becomes another path to uncertainty reduction in the case where you're anticipating future surprises that may happen. It's a very successful strategy. And, social systems are all about uncertainty reduction, or like spreading out the uncertainty among different people who can all explore in different ways. We all have different personalities and different things we do, and we can come back and share those beliefs. So that's kind of how I tend to view it, is that it's sort of an emergent property maybe of basic physiological needs that have blossomed into something much more complex in human brains.
Yeah, I mean, one thing that is apparently a sophisticated feature of cognition is future planning. Mm-hmm. And I was reading Sarah Hooker's book around, she was talking about these compute limits on the executive order in the US. But anyway, she had a lovely little history in the intro where she was talking about, in the 1600s, after we had like the Great Fire of London and the Great Plague and stuff like that, we actually started thinking about risk management.
Yes.
We started thinking about, there are bad things that can happen in the future, and actually we should start, planning and sort of, instituting governance and doing preventative measures and like washing our hands and stuff like that. And that's a kind of societal phenomenon, but presumably in our brains long before that, and certainly in the brains of mammals, we had this predictive architecture. Mm-hmm. And when the future-facing architecture is baked in, then this set point management in the future actually leads to this exploratory behavior. So it's almost like the whole things just fall into place.
Yeah. That's really, really, really wonderfully put. I think and it must be very true. I imagine in just, older civilizations, whether they're nomadic or, agricultural based, at some point you have to start thinking about safety and behavior of a whole group or, group of people. And that's where I think this exploratory behavior and curiosity and, exploring your environment would have probably become part of human civilization.
Very cool. Very cool. Just before we close out, I mean, we've got a Patreon discussion as well, and folks at home should listen to that, because I remember it being very good when we were talking about agency. And I've been trying to avoid talking about agency recently because, the audience are frankly sick of it because we've been talking about it so much. But I remember we did have a very good conversation about agency. I mean, is agency real?
It feels like a loaded question, and by design. So I'm gonna do the pedantic thing and ask what do you just to understand your definition of real in this context here?
Yeah, is it an as-if property? Is it again, I'm making up terminology here, but I guess like an agency instrumentalist might be someone who thinks that it's a bit of a useful fiction, but it's not real in any sense. But as we were discussing earlier, what does it mean to be real if the phenomena does everything that you expect it to do? Then how could you say it's not real?
Right. So I think my answer is similar to the kind of the sort of model versus reality sort of question that I brought up before, the model and target system, in that I think it's a useful abstraction that is good at describing the kinds of models that we talk about in the context of neuroscience and so on. So for me, real is more equated with its ability to be a useful descriptor of some thing that we're trying to model. I see that could be as if, it may be literally what's happening. I don't think we can know that. I think it has to be as if is as good as we can say. And I definitely feel that agency is something that is, present in all the kind of models that are able in some way to alter or control the external environment. I would describe that as some level of agency along a spectrum. And of course, when you start getting into anticipation and planning and other things, it's a more complex form of agency. Does that answer your question?
Yeah, it does. Okay, so I think we agree on that first step. So it's an instrumental thing. Yes. It's a model. It's not necessarily. And when I say real, of course, it's not. It's a non-physical abstract concept. So What could I mean by real? Well, maybe I'm not even sure myself, but maybe I'm alluding to it being part of the physical makeup of the universe. Maybe like if someone like God created the universe, maybe they were doing symbolic AI and they've coded up a computer program and they've got an explicit concept of a goal, right? And they said, okay, we're going to have all these little agents and they're going to have these goals and this intentionality and this is the causal structure, and maybe we're just kind of, even though the universe is generated and emerged, we as intelligent agents are kind of introspecting and we're pulling out that original structure that was the makeup of the universe in a Platonic sense.
Yeah, I think that's kind of a distinction that I would draw, is like it's a description of something that I think is real, but it's a description of that thing. I don't know what that real thing even means because I'm bounded by my concepts in my mind, whatever that is. But it's describing something that is in some sense real because we are able to, actually interact with what's around us. There may be other descriptions or better descriptions or alternative ones that still describe that same real thing, if that makes sense.
Yeah, it does. And I kind of agree that they seem anthropomorphic. So, we're bounded cognitively by the knowledge that we have.
Yes.
But then again, the knowledge we have was endowed to us by the laws of nature and evolution. And it's entirely possible that there's this weird resonance that evolution has actually found in a meta sense, has found the modeling framework that was used to create it. Mm-hmm. So there's almost like this information bottleneck that you can just start the universe again. Maybe there's a Goldilocks zone, but it'll lead to the emergence of the self-recognition of the very primitives that went into building it in the first place, which is quite interesting.
Yeah, I mean, this is kind of, it speaks to the idea of the cybernetic idea of like, you become a model of your environment. So does that mean you're recapitulating what is real now in this model? Like it's not just as if, right? I think what I'm trying to draw the distinction is like scientific models versus models in our mind. That is a very similar kind of thing to me. Like it's just a different way of doing the same kind of thing, of modeling something that's real, but kind of at a meta layer of that, right? Because the scientific models are based in our models of the world that we are now modeling other parts of the world in a very specific kind of way. So I do feel like there's definitely, if there wasn't a connection to what is real, we wouldn't be able to operate in the world. So I think there is definitely like some convergence in there somewhere, but I don't know how deep that goes. There may be things that we uncover about the universe that we never expected that we can never model. And then in that case, then it would be that our brains behave, or even our scientific knowledge behaves as if, but I find that to be unlikely that it would be that way.
Yes, but it also goes to the abstraction and canalization point that we spoke about before. So, there's all these levels of emergence, yet we have converged on this shared epistemology. I mean, of course, it's very divergent in many ways, but some of it isn't. Mm-hmm. Some of it feels very universal. We understand each other and it describes the universe extremely well. We'd be forgiven for thinking that it was Platonic in some way. Yeah. And certainly some abstract knowledge probably is Platonic because it really is universal. It works in all situations. But so that's that. But then there's the question of, okay, so it's just an instrumental description, but people then use it to explicitly build AI systems. That's what GoFi people did. They said, okay, I'm going to build an agent and it's going to have these goals and it will create these sub-goals. And these are just explicit things that I've designed, or maybe they've been meta-learned or something like that. And now you're actually using the abstraction as the primary representation. Or in philosophy, like in Nick Bostrom's work, with instrumental convergence and orthogonality and so on, the goals, which are these instrumental abstract objects, are now becoming the basis for theory. That we're making statements about what happens when AI agents have a certain level of intelligence and what kind of goals and intentionality will they have. So it feels to me dangerous to take something which is an abstraction and then use that as the basis for theory or building AI agents.
What way is it dangerous to you?
Well, dangerous in the sense that, I mean, maybe I'm talking about two things there. So, using it as a basis for theory and philosophy and using it as a basis for building AI agents. So maybe we'll do the latter one right now. So, GoFi never worked particularly well, but there are still loads of people who strongly believe that we can build symbolic AI systems that do explicit reasoning and planning, and certainly for a specific set of tasks, planning is a great one. They work significantly better than current AI systems. And we're seeing neurosymbolic approaches that blend the two things together. But these are things potentially where we have an explicit goal. And what is a goal? Well, it's just presumably a future world state. But that's kind of brittle, right? Because how do you explicitly, in the complex world we live in, how do you explicitly and robustly represent a future state? Now, we seem to do this because we have this way of just talking about future situations, and our representation overcomes a lot of the brittleness. But when we start coding these in computer systems, it seems much harder to do that.
So you're saying, is that where the risk comes in, and that making the assumption that these systems are the as if versus real, and we'll quickly see the limitations of our own models, and if that as if versus real boundary is as true as we think it is, when we start applying them to the real world and seeing if they really behave in the flexibility and in the way that our own models, internal models, would in the same situation?
Well, yeah, in the sense that in the physical world, as we were saying earlier, we have a symphony of diverse, complex processes which run, and then they lead to future situations, and there's all sorts of convergent and divergent behaviors with chaos and all sorts of stuff like that. And we have the ability to kind of categorize patterns or modes of that future state space, and we call it a goal. Yeah. And we then put that goal into an AI system. And as we were saying before, this might work. Maybe it's possible to represent a very complex physical system using a very abstract computational model, and maybe that will work. But maybe it won't. Maybe we are we're underestimating the amount of categorization and robustness that we use when we think of a goal. And we're actually reifying it, and we're stripping away all of the actual cognition that we're doing.
Yeah, I mean, I think that is a risk of having our models being way oversimplified. We may not know where that limit actually lies. And I think the only way we can know that is by actually trying to apply it in the real world, which to me is a good benchmark of how successfully our models have really captured reality in the first place. But I definitely agree with you. I think that's probably something that we're going to see as we deploy more agents into the world. The limitations of the models that we have may become clearer to the degree for which our models are truly representing reality or behaving as if they do in a way that's not quite in line with what is really happening in reality, that our minds, our brains and our collective knowledge we take for granted for what we have in our models.
So I've been very skeptical of AIX risk, and my main reason for that is I don't think current AI has any agency. I mean, in a sense, I agree with them that if there was an agential AI, that was a super intelligent, that would be something to worry about. But I don't think current AI is. But what do you think about the future of agency in AI systems? I mean, does that concern you? And I mean, my definition of agency is, like strong intentionality and self-causation. So if we did have AI systems that exhibited that, would that be an overnight thing? Would it emerge from, would there be some kind of, I don't know, maybe cyborgs or human computer symphony, collective intelligence, and then would it diverge? How do you see that panning out?
I think there's a lot of, money in AI right now and push for a lot of focus on developing. We haven't really, got to a point where there's a huge push for agency yet, but some of that is going to be really useful, I think, like in industry and manufacturing and things like that. That may be the beginning of it in autonomous vehicles and stuff like that. And maybe then it will, continue to be further explorations of this sort of, cybernetic relationship between human and machine that I think is probably going to emerge in the next 2 decades or so. The part that worries me with the intentionality and agency aspect of it is the degree to which the models and research moves and the money that's in it relative to our understanding of the limitations and risks and ethics and the legal system of what's permissible. So I think we are going to move in that direction, and I don't think there's anything that's going to stop that. And I don't have nightmare scenarios that it's kind of popular in science fiction. I think I'm much more worried about people and us developing systems or hooking it up to things that are, mission critical systems that are decisions that humans should be partly involved in. And that level of agency, we should be careful as we're designing them to make sure that they don't get into the wrong hands, that we have the correct laws around the operation of that equipment. And I am worried that if we are moving too quickly at the rate at which the law and our understanding of these systems catches up, there may be some kind of event that has to happen first before we learn what we need to do to actually regulate and control these systems properly.
And on that, do you lean towards safetyism, which is to say we should do risk assessment and we should prevent bad things from happening before they do? Or do you lean towards libertarianism, which is to say we can't really adapt quickly enough, and if we just trust the thing, then safety will kind of come out of it?
I think I'm a bit too cynical to believe that latter point, because I do feel like the incentives right now for companies isn't necessarily in the risk side of things. I do think there is some level of self-regulation. There is a growing interest in AI safety, interpretability, and explainability, these kind of things that are definitely present. Some companies do at least have ethics committees. I don't always know how, if that's just for show, but they do at least exist, and there's some thinking about it. I think I put myself somewhere closer to the center, slightly left, maybe, where I do think I believe in the ability of some level of, we can't necessarily know and adapt in time anyways, but it is safer to still be having the conversations and putting some safeguards in place, and having them at least there and having the discussion continuing rather than being way on the far end of the libertarian end of that spectrum.
Yeah, it's so worrying because about to say worrying, I don't know, to be honest. But I mean, certainly when we start to augment ourselves with technology,
Yeah.
I know a lot of people criticize transhumanism because it could potentially lead to massive disparities in society. But also, in a more diffuse sense, when we become a collective intelligence where we are entangled with AIs, just like in the animal kingdom, that there's a relationship between the collective and the agency and cognition of the individuals, like in ants, for example. And ants are quite dumb because they form a collective. And when we become a collective entangled with AIs, it could easily reduce our cognitive capabilities, like our agency. And of course, we're just purely speculating here, but there is a potential future where that's quite concerning. But is that something we should regulate against, or what should we do?
That's a great question, because I think this is the same kind of thing with any industry, regulating it versus, do we make people make their own choices, versus do we intervene, in terms of any kind of governing system. And I think I find myself, I think that, speaking of agency, we are free agents. We are able to do and make our own decisions. And I do trust that people, generally are somewhere in the range of their best interests, but not always. So I have some level of, I'm not on the extreme end of that, but I do worry about just the incentive structures of companies. That's really where I think it's driving it, is that's where the money is. And that's what, we're moving forward with that incentive structure. I think that we definitely need to have these discussions, and the legal system needs to be paying attention to it. But I think there's, we don't know what the consequences will be. I love sci-fi and fantasy and stuff like that. So the ideas of having this transhumanism and, nanobots in your body that will destroy diseases, all these things that you kind of, it excites me on a fantasy level. I know that's just a fictional representation of what the reality could be. And I don't know what that would look like in actual society. And I don't think anybody knows. I don't know how anyone's going to react to these things, even if they're done in the most beneficial way possible. We may find out some things about our human nature that we didn't realize we really required or took for granted. And so it excites me on a theoretical level, but I definitely feel like we need to be talking much more openly about these things, and having enough regulation that allows for growth, without having too much that it stops the research in general. And now, where those boundaries lie, I feel like that's not my expertise. That's kind of a high level answer to a very complex problem. But that's where, if I would draw the kind of put the line in the sand somewhere, it would be, maybe this is too on the nose, but some kind of, enough so that you can have that complexity, and enough that you can have that adaptability, but not too much that you become restrictive. Kind of talking about dynamics and systems and things like that. I think that's always the best place to lie.
And I spoke with Pedro Domingos. He's a bit of a controversial guy, but he was advocating. He's obviously a libertarian and an accelerationist. But his basic thing was that, if you look at the way markets work right now and traders, we actually have AIs. We have AIs that act on our behalf, and the AIs share information with each other. And there's this kind of equilibrium in the trading markets where certain thresholds are met and trades are made, and the whole thing just balances. And we don't really understand how it works, but it doesn't matter. It just works. And he was advocating for a kind of governance like that, where we all have our own personal AIs, and it's much more of a direct democracy when the AI can actually understand what we want, and we can be far more dynamic and so on. Does that seem dystopian to you, or do you think that's a good idea?
I feel like a lot of these arguments feel like kind of the invisible hand sort of thing. It's I mean, it doesn't really. I think Richard Thaler called it the invisible hand wave, which I feel like is to be.
This is a reference to Adam Smith, of course, the hidden hand of the market. Yeah,
right. I mean, I think that's. I mean, I don't think we know. I don't think I don't think we can confidently state that's what's going to happen. And I don't know if, it depends on your level of what you think is a good measure. Is market all that, what about people's overall prosperity and things like that, and people's general perception. Like even right now in America, right now, like the economy is doing well, unemployment, but the general feeling of a lot of people is not great. And then that may be due to other factors that are not necessarily directly linked to the market. But I'm just saying that when you have an economic measure or something like that, that may be a future you look at, but that doesn't necessarily mean that you understand all the dynamics of what other things are affected. The world is very complicated, and there are all these other factors we have to take into account. So I would say I'm not that optimistic, but I don't think there isn't some truth to that there isn't some level of this kind of self-regulation that will probably occur naturally, because we are also incentivized to be looking out for our best interests. The problem is I think the systems that we are now studying and interacting with are so complicated that we may not be able to, even when acting in our best interests, know what the outcome is going to be. And I have advocated this is kind of, this isn't something that I would say is possible yet, and it would require a lot of really good data collecting, very accurate data collecting, but it would be very interesting to me to move toward an effort of predictive modeling on the scale of like complex systems where we make public policy decisions, and you do something that seems like a great idea. What are the outcomes going to be? Oh, well, I didn't expect this to destroy an entire class of people, for example, even though it looked like a good policy on paper. Kind of the unexpected consequences sort of scenarios that happens a lot when well-meaning people put forth a good policy that ends up hurting or harming other people as a result. If we had ways of predicting incentive structures, like how can we incentivize people to make monetary decisions, companies or individuals, and show them that if you made this decision versus this one, you would still benefit society or benefit a group of people, and there would be no net loss to you. Like, can we make better predictions as companies or as individuals in a complex system that requires not just social and economic markets, but also the environment and, whatever is going on with our planet and things like that, which are all kind of interlinked now. You need so much data to make a predictive model actually work with something like that. But I do think like that's one way we should be putting our efforts toward, if we're going to be developing AI models, is developing something that has the capacity to reason in a very complex setting using our collective knowledge as people, so we can make better predictions that may benefit the planet and benefit ourselves.
I want to talk about the strange bedfellows in the FEP adjacent community. So this is something I noticed coming in straight away, that there are lots of crypto people. And these are people who believe strongly in decentralization and, almost like they want to have a small government. They don't want, they presumably don't believe in safetyism. They don't want any interference. And then there are people who have the complete opposite view, like a lot of the activists, for example, and they think in terms of systems and collectives and so on. And, one school of thought is that we could just build these distributed systems and good things will emerge as a result of it. And I think I asked Carl Friston this question a couple of years ago, and I got the impression that he kind of lent in this direction. And then there's loads of discussion of when we design FEP systems and we use them for managing smart cities and countries and stuff like that, that we should institute a governance framework on the top. What do you feel about the dynamics there in the community?
Yeah, I mean, this certainly gets into some discussion also like on the spatial web and other things that are, talking more about governance systems and, what the future would look like. I personally haven't run into, I've seen a little bit of talk in that direction, but I haven't really paid too much attention to like the political angle of how the different perspectives have looked at things related to what you're describing. But I will say that it does concern me that that there would be this level of confidence that, like, I understand from the free energy principle perspective, like there's this sort of survival aspect, right? Like, we'll find our way to our attracting sets. It's going to be okay. Like it'll happen. But also you think about like the way that our bodies and minds have evolved. It took 1 billion years and a lot of organisms died, So yeah, maybe it's possible that yes, eventually it will self-regulate itself, but at what cost is that, are we going to incur along the way? Is that something that's going to be straightforward that, or could there have been a better path that would have been a bit safer, maybe slower and less efficient, that would have incur less of a negative loss? So, I mean, and, there is a history of civilizations destroying themselves. That's happened hundreds of times, of civilizations eventually just dying out, whether that's from, warfare or other things they did. And, I just wonder if we can be so confident to be on that complete deregulation side. Although I understand and definitely respect the nuances of the other questions that come with that, which is like who regulates and who makes the rules. And there's so many other things that go into this that it's hard to, formulate a complete answer. But I would say I still lie on that perspective that I think you need more than just this putting all of your hope into self-regulation as being the primary component to drive decision making.
Yeah, I mean, I hosted a debate between Beth Jesus, Guillaume, the extropic guy. And he's actually interesting because he also has a startup, talking about the physics of AI, very similar stuff. Yeah. And he was debating Connor Leahy. And obviously, he's an accelerationist and he was making, all of these, we should. Connor, at one point in his best style, said, "Oh, what? We should trust the void god of entropy?" Yeah. Because he was basically arguing that good stuff just comes out of all of this. But I'm a bit of a centrist, and I mean, clearly, I think it was a good thing that we banned smoking indoors. Mm-hmm. But now in the UK, they want to ban smoking in pub gardens. And that seems like an overreach. And sometimes in retrospect, we look back and we think, yes, it was a good thing that we banned that. But clearly markets have failure modes. And, sometimes it's good not to regulate because it increases velocity and innovation. And sometimes it's bad to regulate. But it's a really difficult thing to get a handle on.
I completely agree. And I think it's only going to get harder. I mean, as our world becomes more and more interconnected, there's more and more considerations to take into account. And I think that's why I was emphasizing this need for, finding ways to predict in complex systems, like that's of course like a pipe dream because the amount of data you would need to do that kind of a thing. But this is the kind of thing is like how much overreach is the right amount of, how much overreach is maybe not the right word, but how much control and regulation is the right amount. And that of course will differ by opinion. I mean, everyone will have different levels of how it affects them. I don't think there are easy answers to this, but I definitely think this is a really, really important area of the technology we're developing that should be taken into account and should be not taken lightly. Because it's very easy to get pulled into the AI hype train. It's so exciting, where it's this amazing time where, all these things. And whenever I'm thinking about active inference, I'm really just thinking about math. Like that's just for me, I'm excited about, I'm writing code and I'm making, looking at math equations and then getting really excited about these philosophical topics, but really they'll have an impact on the world and they really, in a way that really matters. And we should definitely consider it.
Interesting. And just in closing, I mean, if you could, you had a magic wand and you could go back in time and you were the government, would you regulate social media?
Oh no, that's a really difficult question. I mean, I think I'm going to be consistent with my prior responses, which is some level of regulation.
Yeah.
Because I don't think inherently social media in itself is a problem. I think it's also the kinds of problems that have emerged from the usage of social media are also a response to the general feelings of people in the world. And they're using it as a way of an outlet. And, for example, if you think about like, controlling elections and some of those things, right? There's that whole angle. There's also like the psychological angle of, how people are using it. Those are all questions I would ask is like, why are people using it to compare themselves to other people and all these other things? And why are they feeling that way? What about our society means that when we have a tool, we use it for a certain purpose like this? And there are no easy answers to that because some of it is just like, that's just how things are right now. And you can't solve those questions by just, they're complex societal problems that lead to that. But I do feel that social media has been really wonderful in a lot of ways too. And it's provided a lot of net positivity to the world. I don't really use it. So I don't, have very little social media presence, at the moment, but I do feel like it's been, amazing, for example, in unsafe situations where hundreds of people have, used social media for communication. It's brought scientists being able to broadcast their papers around the world. It's the ability to share knowledge and information, which is what everyone got excited about with the original internet. So I don't know. I feel like that's a hard question to answer. And I think I would go with the response that I think some level of regulation, would have been useful, but it's always hard to know if that regulation, even if done in good faith, would also lead to more calamitous outcomes that you would not have foreseen because you're imposing a regulation. And this is kind of a black markets and other stuff. These things happen. So I guess the way I would put it is that I'm glad that I'm not in government itself, but I'd be happy to contribute as a researcher from the outside. But these are hard decisions, and I don't envy anyone who's in the position of having to make them.
I don't. It's certainly true that regulation done badly is even worse than no regulation at all.
Absolutely.
And I agree it's very complex. There are failure modes of social media. It's a good thing, and in some ways it's a very bad thing. And when you start banning things, when do you stop?
Yeah. And who decides?
Yeah.
I mean, it's the same thing with free speech, and there are other questions that we have too. Is well, what speech is permissible? There's a kind of gray zone of there's certain things yelling fire in a crowded room, or So I don't know. I think there's in legal systems there is the principle of least harm, where it's sort of you have some level of laws that will it'll harm some people, but on the whole it's good for everyone. But that's going to get harder and harder to compute what that looks like, I think, is the problem. But I think that's kind of where I would tend toward, is just enough that it has least harm without also at the same time incurring, stopping the accelerationists at the same time.
So active inference is quite inscrutable for people coming into it. I mean, I know when I did the first Carl Friston interview, I was reading some of his papers from about 15 years ago, and they were remarkable in the sense that they were bringing together so much jargon and terminology from different fields, from neuroscience, from cognitive science, from physics, and it was really inscrutable. I felt that some of his mathematics was a little bit difficult to get a handle on. What was your journey into active inference?
So my journey into active inference started in 2018. I was trying to write a grant. I was actually in my first postdoc and realized that I was wanting to leave academia. That's when I moved into industry. And at that time, I discovered Carl's 2013 Life as We Know It paper and was very inspired by it, but I didn't understand any of it. And so as I dug deeper and deeper, it just was this endless hole of finding new fields that I didn't know about, that I had to keep looking into and researching and learning more and not knowing where to stop. And so that continued for about 3 years of just exploration and the same kind of thing that you're saying, reading these papers that just pull in so many different topics together. Everything just seemed very inscrutable, as you said.
Interesting. So, I mean, tell me more. So, how did you build a mental model of this? Because I think it's really difficult, because active inference is an example of a discipline where you have so many different folks from multidisciplinary backgrounds, and that's different from something like machine learning. So, do you feel that you've focused on one of those backgrounds? So, let's say coming at it from a very technical perspective, or have you embraced the full spectrum?
I think I'm getting closer to embracing the full spectrum and coming at it myself. Since my PhD work was in neuroscience, I had that neuroscience background, which, even though there are a lot of other topics that are brought in there, the core of it is neuroscience. So that gave me a good anchor, but I wasn't at that particular time as well versed on the technical side of things. And I was actively trying to learn that anyways, as I was transitioning into industry to be a machine learning engineer at that time. So it was natural to start slowly bringing in all these ideas. So I would say that, there's a lot of the areas in active inference also involve a lot of the philosophy and cognitive science that I don't know as much about. More of the neurobiology and the mechanistic side of it, as well as now the technical machine learning side. And I've had to slowly pull in these threads as I've learned more and more about the field. I was in a neuroscience lab. We were doing computational neuroscience. I was working with Dr. Ken Kashida, who's at Wake Forest in North Carolina, United States. And we were doing some work modeling human behavior with reinforcement learning. So it was an adjacent field. But at that particular time, I had the neuroscience background, but I did not know about active inference because it was relatively niche at that time.
So you have this vision to, essentially educate up and coming scientists on active inference, because it's really, really important. Why the focus on education? Why do we need this?
I think the active inference field, if you kind of look at the sort of genealogy of how it's developed, and also into new ideas like the free energy principle and Bayesian mechanics, are these new terms that have also emerged alongside active inference. There's a very, very historical perspective you can take on the field. And when you look at how it's emerged through time to where it is, there's no good entry point into the field. But at the same time, I see active inference as being really revolutionary, in the same position that deep learning was in the early 2000s, where there are a lot of interesting ideas and papers out there, but the explosion had not yet happened. And so because we are perched on this precipice where we're going to start seeing all these new and important ideas come out of active inference and provide it some sort of challenge to the way that deep learning is currently done today, I felt it was really important to have a very clear resource that would guide readers through the field that did not have the neurobiology focus on it. So just looking at the core mathematical mechanistic ideas, but also the implementation, so that I can bring it to a much wider readership, both for newcomers and students, undergraduates and grad students, but also for researchers, engineers, and machine learning engineers, or robotic engineers, and any of those sort of applied fields that use these kinds of ideas.
And what are the high-level things you talk about in the book? And of course, this is the first edition. You've got another edition coming out next year.
That's correct. So there are going to be 2 books. They're going to be separated for focusing just on active inference. And the second book, which is going to be submitted next year, is going to be on Bayesian mechanics specifically. So there's a nice demarcation between those two. So for the active inference book, the basic idea is to cover all the fundamental concepts and themes you need to know. So starting from just the basic way of how can you think about modeling this interaction between agent and environment in a statistical setting. So that requires just a change in perspective from how normal statistics is actually done, so you can see that relationship work and then begin to build models from that. Starting, there's 2 versions of active inference, one in continuous time and continuous state spaces, and one in discrete state spaces. So the book provides all the fundamentals of the background you need to know, things like predictive coding, variational Bayesian inference, connecting latent variable models with more common parameter estimation models, and then leading into the core of active inference, describing all the key papers and the state of the art. And then the third part of the book goes much more into extensions, where the field has gone next, how to apply it to different areas in a historical perspective of how all the different antecedents and also influences of active inference kind of coalesce together in this sort of nexus where active inference lies at the center of all of it.
Yeah, you made an interesting point, which is that we might be on the precipice or something. So it might be like the the ImageNet moment back in 2011, and back then we had these sophisticated algorithms, but they were very difficult to do. I mean, the only top folks at Google were doing them. You needed lots of compute power and so on. Is that analogy the same for active inference? So how useful is it now, really? Like, how good do you need to be? What kind of tools and software do you need? How does it work?
So for active inference, as its origins were in the behavioral neurosciences, so a lot of the early models were designed for very simple experiments that did not have hugely complex environments. So there has been some work trying to look at scalability from the perspective of amortized models. So using neural networks to learn parameters, to kind of bridge that gap between the active inference world and the deep learning world. This is kind of a bit of a hybrid approach, and that has shown some promise in some areas for scalability. But where active inference is right now, the current software that's available, PyMDP, for example, is the primary software. There are others that are sort of related, like RxInfer, that do similar kinds of things. We're at kind of this interesting point where we are poised for this kind of expansion into this highly more scaled space and applicability, because there's been a lot of papers looking at robotics, for example, performances between active inference and robotic methods, or between active inference and reinforcement learning. But there isn't this is sort of why I like to make that analogy between deep learning around 2006. It's getting there, it's comparable, and there are lots of really interesting ideas that are there that show the high potential for active inference, and we need more people to come into the field to develop it. And that's the motivation for writing this book, was to get that wider readership involved.
Yeah, that's really interesting. I mean, I don't know, quite a few people in the Discord community are just saying to us, how do I do this? And many examples come up, like, I want to build a multi-agent system where the agents exchange information. And they cite this agency as being one of the reasons to use active inference because, of course, in the olden days, we used to write software and we used to write for loops and, we had conditional logic and stuff like that. And we were explicitly telling what to do. And then machine learning was trained with data, but it was still pretty much just a static model. And once you've trained it, that's the end, unless you do something like active learning. And then now we're talking about active inference, where we have essentially an agent that can continually learn and adapt and exchange information with its environment. But that seems quite scary, right? Because how do we make it do what we want it to do, and how do we actually code it with software?
So I think that's the key mechanism that you point out, this engagement with the environment. That's the key feature of active inference, the ability for it to, going out and to seek out, certain preferred or expected states, which I'll use that term instead of rewarding states. That's much more in line with the active inference perspective. In the active inference literature, the simpler models, they follow this paradigm, but it's a framework. So there are certain perspectives and ways you can design these models that have that behavior in there, but that doesn't mean we can't augment them with other features and things that are really necessary for specific environments, where we can add in our own controls, add in human knowledge or our own, I'm using the word biases in a neutral sense here, but if we want to bias the model to do a certain type of thing, it's not like we're going to lose the controllability aspect of it. There's still a way for us to inject in our own set of particular goals and things like that into the model. It's just that the model has the ability to be very generalizable and applicable to many different types of modeling situations, but we're still able to control aspects of it.
Yeah, in governance, we have we talk about Goodhart's law, and we talk about things being good-hearted. So as soon as we try and ban things or control things, we completely distort the system. It's when a measure becomes a target, it ceases to be a good measure. Do we have a similar thing here, right? That we have these agential applications, if you like, and when we try to steer it or enforce goals, then it almost, I don't know whether it's a binary, but it very quickly loses the very thing that we wanted it to have in the first place, which is, agency and dynamism.
So if you look at active inference agents, this is a problem that's also present in reinforcement learning, where there's, a combinatorial explosion of different kinds of paths you could choose. And to be efficient in active inference agent, and indeed humans as well, there's only a subset of particular paths that you might choose in an environment that are relevant for a task at hand. And I think the same sort of principle applies in that there's no way you can, explore that entire search space anyways of things you could do. And there may be certain things we would just discount as being certain paths that are just not interesting to the agent. So this is a kind of agent that would not pursue certain types of goals. And so those would be things that just would be a very low probability of being selected by that agent. So you can still maintain that flexibility of having an agent that's able to choose what it's going to do, but you can restrict the search space within which it's going to make those decisions.
Very cool. But just on the goals thing, though, where do the goals come from?
For the active inference agents, you mean?
Yeah, so they do planning as inference, right? Which is a form of, de novo goal generation, if you like, and then we constrain the trajectories of goals as a form of design of the system, and we hope that it maintains flexibility, but it still does the thing we want it to do reliably.
Yeah, so I think this is kind of going into the distinction between when you design simple active inference agents, where we are specifying some of these boundaries of, what is the agent capable of, what does its state space look like, what are the kinds of things it can do, versus a true active inference agent, which is where the field is moving now with work in structure learning, for example, where it's learning its own goals and learning those specifications itself, rather than, the user handcrafting the components of the generative model. So, as we start getting more into that space, I think that question is going to become more and more relevant. We're going to have to consider what kind of agent would emerge in that sort of scenario. Under the free energy principle, we have some ideas about agents that would emerge from this would be agents that are trying to survive. That's sort of the biological imperative or the biological influence from the free energy principle. But I still think it's an open question of how these agents are going to behave when you start building models that are this open and that's going to be an open area of research.
Yeah, could you go into a bit more detail on that spectrum? So, of course, in the natural world, all of this emerges from lower level dynamics.
Mm-hmm.
But when we design these systems, certainly with active inference now, we make the agents explicit.
Yes.
So it's a little bit like old school symbolic AI or just doing any Bayesian modeling. I create all of these variables. I give them names and I represent structures and the causal relationships between them. So that's how it is now. But you're kind of hinting at an evolution of that where it could do some of that stuff by itself.
Yes. Yes, absolutely, and that's essentially what we can do. We can infants are great at this, and we are also, especially infants, because they have less priors to work on. They have less prior knowledge about the structure of the world. They have to start creating these categories and also mapping things. I'm using the word metaphor kind of loosely here, but metaphorically saying this is like this other thing, and so I can use the same properties to sort of link them together and map one model onto a different model, and leverage that information I learned somewhere else to something that's similar. And so in some sense, the priors and the inherent nature of those agents, their self-model, that has been crafted by evolution. So I don't want to use the word too teleologically. I just mean that evolution has produced an agent over time that happens to be the kind of agent that expects to be in a certain kind of environment, and its preferences and habits and things like that have been sculpted through its evolutionary history, which is, you can think of like compression of billions of years of supervised training in one agent's DNA that unfolds with time as the agent develops. So when even though the agent may we might say that it's it is inventing categories and things and learning about the world, first of all, it is of course constrained by evolution and all of that that's come prior to it. It's not like a completely blank slate. But in addition to that, there's also supervision through parents and culture and other things that also kind of restrict its space. So when I see active inference agents that we're building, I think the analogy is very similar. We are sort of the evolutionary benefactors in a way of where we can sculpt in certain types of what do we want this agent to be. And within that space, it's still free to explore and choose its own goals and acquire preferences and personalities and things like that. But it won't be like a completely open space. And I think it's going to be hard anyways to design agents that are completely free and open. You can probably get all kinds of aberrant, interesting behaviors that you may not actually want that would just emerge out of it. And there's active inference researcher Noor Sajid has done some work in this area as well. Learning in active inference, we call it prior preferences, what the agent prefers to do, and that would be probabilistically what it expects to be doing. You can get some very strange behavior depending on how you determine that system. So I think there needs to be some guidance from us as creators of these systems in order to even have a successful agent in the first place. And I think that's analogous to how evolution and growing up with parents and society and things like that also sculpt us in a similar kind of fashion. When you start talking about these higher level, more abstract things that influence us, so society and culture and just the general rules that we follow, I think what they don't constrain us physically per se, but we learn about what is permissible is what's expected. So we learn what to expect about the world, and we sculpt our world in that way to make it make sense. Some of these may be cultural rules that are just part of, this is the expectation of how you behave in this society or this family or this culture. And I've actually just been traveling to Europe, and I always look up, before I go to a new country, what is expected of me? How do I behave, right? Because you can get into interactions that you wouldn't even expect, things that would seem aberrant to someone else because their norm is in a different direction than yours, but then to you is totally normal. And so there's the cultural aspect as well, but there's also even just like traffic laws, for example, like learning in a new city, how do you behave in the city? And then for the people who live in the city, all those items are all predictable things. Like I have a stop sign, and it makes the world make sense to you and makes everything much more efficient because you don't have to think about them. They're just these assumed priors that are just part of your generative model. And so I see them as those sorts of ideas don't constrain us physically, at least not directly, but they're still in some sense a physical constraint because they become, in a more abstract way, because they become part of your just narrative about how you see the world that can be very unconscious. And you don't even think about how you behave. You just know your brain wants to be efficient. This is how you unfold these actions. You don't have to think and calculate, every single piece in detail about certain things. But that in itself is a kind of physical constraint, because it would stop you from doing certain kinds of activities, not directly physical in when we talk about the slower level, but in some sense still physically stopping you from doing something unless you make the choice to, well, I'm going to violate this rule that's expected of me in this society or culture or something like that.
Yeah, I'm really interested in this kind of hierarchy of phenomena. Right. So, obviously we have the physical world. You can take certain lenses like the selfish gene, right? So you can think of genes and memetics and you can go all the way up to culture and language and so on. And as you say, they're actually entangled. They're sharing information with each other. And we seem to somehow model all of this, right? So, we know how to behave physically and verbally and culturally when we're embedded in different societies. I mean, how would you build an active inference agent to know how to behave well in Italy?
So I think that's an really interesting question, because I think the first thing you would have to do is, the actual things you would have to teach the agent. You could, in some sense, I want to say the word program the agent and just say, like, here are the things you should do. But if you have an active inference agent, the way that I would design it is the same way that you teach a child. Italians who grow up, Italian infants, when they are in the world, they come in with some pre-existing knowledge, of course, about, space and time and some, basic abstract principles about how the world works. But all the cultural layer that happens to them, between the ages of, 0 and 5, you kind of, probably even earlier than that, an infant by the age of, actually, this is just by the age of like 2. I was just thinking about I was just at a cousin's wedding, and one of my cousin's children is, she's maybe a year and a half, and she met one of her friends, playmates, and they put the two of them together, and they both kind of very tentatively kissed each other's cheeks. And they're, they live in Switzerland, and so they have these sort of cultural norms. They've just been watching their parents. They know, okay, this is what's expected of me. My parents said that when I meet another person, my peer, and, we're interacting, this is how I'm supposed to behave. And so I think the same thing would be true of an active inference agent, and even robots that don't have priors to begin with. You look at how infants learn behaviors, and you can just teach the active inference agent those things. So it's sort of feedback. It will grow and learn. There's this huge space of possible actions and things that are behaviors I could do, but I'm learning that according to the culture, Italian culture, in your example here, these behaviors are more permissible than others, and this is how I'm expected to behave as, to be a bit facetious, an Italian active inference agent. These are some of the things that are expected of me within the context of my culture.
Yeah, good old imitation learning.
Yes. Yeah.
That's quite interesting philosophically, though, because that is kind of pointing to behaviorism. I mean, a lot of people say that even reinforcement learning is a kind of modern incarnation of behaviorism. And it's really interesting from a cognitive science perspective, because, is the only thing that exists the behavior, right? So, the children kiss on the cheek, and then something happens inside the brain, right? Or inside our minds. How does that process happen? So by purely imitating the behavior physically, does that trigger some commensurate representation or thinking inside our minds?
I would say so. So, I mean, we take the language of active inference is all probabilistic. So there are certain things that can happen, a nearly infinite state space, but some things are more probable than others. And so the things that are more probable are what we expect. So, I can imagine that infant's model through imitation is being refined over time as it interacts, and it's told, here's how you're supposed to interact. The interaction of kissing as a greeting is becoming a higher and higher probability or expectation under that infant's agent generative model. And so that is the kind of, there is an internal development that's happening where, every single time you meet someone, that's the expectation of what's supposed to happen. And that's the most uncertain situation. So if you didn't get it, didn't get that kiss from someone, perhaps you'd be confused, and then you may learn there's actually more nuanced things. There's other cultures that don't do it, or, there are other situations where it's less permissible. There are certain, subsets of different types of situations where the certain behaviors applies, and then you get to learn the nuance about how culture, which is very complicated. Sometimes the rules apply in one situation, but not another, and, depending on the parties involved. So I think this is all building that generative model and building the probabilistic model of what's the most common expectation of behavior that would all happen internally, but then also through feedback. Receiving or not receiving something after executing a behavior will teach that agent all that fine graining of the nuances of the different situations in which that behavior applies.
Yeah, ever since I discovered externalism, it's something that's preoccupied my mind quite a lot. And I guess you could take a radical view and you could actually argue that the behavior itself is the locus of the cognition, and that the brain is just an impulse response machine. And, it's almost like we need to look outside the brain to actually understand cognition. But certainly there must be some symmetry. So if the behavior is present, certainly in the presence of sophisticated brains, then there must be some representation or resonance or transfer, but it's about what came first.
Yes. So I definitely think that, that is kind of the key insight of active inference, which is also present in, fields like cybernetics, but being able to become a model of that system outside you. So it's always, relative to what you experienced and what's part of your cultural or ecological niche where you're adapted. But those things, I think, must in some way, it's just more efficient to have that model, because you don't have to think about and plan your actions in a really complex way. If you already know what's permissible, you just have to look at situations that deviate from a norm. And then try to understand those deviations, why, they may make me feel a certain way, and then understanding those deviations of uncertainty from that expectation helps you better adapt in new situations in the world.
Yeah, because people talk about biomimetics, and that simply mimetic simply means copying. And isn't it interesting that even in lieu of sophisticated brains, like even in plant ecosystems and stuff like that, information is being copied all the time, right? Not only genetic information, but also simplistic behaviors and, growing towards the sun and stuff like that. Isn't that fascinating?
You mean the aspect of convergence, that different types of creatures in different environments can converge upon similar types of behaviors or mechanisms? Is that what you're referring to here?
Yeah. So I suppose at different levels of agency, you see, different types of information sharing. So at the very lowest level, it's simply just gene mimetics.
Yes. So I think that speaks to just how effective that strategy is. We are isolated agents with limited information, and but we are able to take in so much from our experiences and our memories. And so being able to interact with others who have experienced different things, I suspect that's why, social cultural animals that have an aspect of social behaviors are very successful. This isn't, of course, there are many, many very successfully adapted creatures on the planet, but many of them that are social tend to develop these higher order or higher level types of behaviors because they can do this type of information sharing.
So can you disambiguate active inference, the free energy principle, and Bayesian mechanics?
So I think this is in general a tricky task just because, the way the field has evolved. So the perspective that I like to take on it, which I think makes the most sense, especially from an education perspective, knowing that sometimes these lines can be a little bit blurred. I see that I look at the top-down level, starting with the free energy principle. So the free energy principle itself is getting into a description of systems, which are dynamical systems of some kind, that are behaving in accordance with the principle of minimizing variational free energy, which is a statistical quantity that agents can calculate. And in general, the free energy principle is a bound. It's a proxy for something else called surprisal, which we can think of, very roughly speaking, as a kind of uncertainty. So minimization of uncertainty, which helps to restrict agents to a specific set of states that are conducive to their survival, states they'll frequently revisit. Among all states they could visit in a state space. So some of these may be, for us as complex agents, it may be cultural layers of it. There may be evolutionary and biological layers that are more specific to survival. But then as you get higher and higher, they also encompass a lot of other kinds of behaviors that seem less directly linked to survival per se, that build upon this. And when you have this basic framework of how agents can behave, and you have the statistical quantity you can calculate, you have a way of describing systems that persist over time and are self-organized in different languages. Mathematical languages, you can describe them. So, for example, you have active inference, which is the application of this free energy principle to the brain and animal behavior. And then you have Bayesian mechanics, which is a much more broader take on the free energy principle as applied to dynamical systems theory. So studying the property of systems which contain interacting variables that change over time, and how those systems stay different from one another from the perspective of statistics. So how they retain their properties. So that's the demarcation level that I see it, as I see the free energy principle as an underlying principle applied in two different domains.
So how has this evolved over the years? Because I'm aware there have been different formulations of the free energy principle, and of course active inference came into play at some point. How did this all kind of evolve over time?
So if you look at the sort of history of these fields, they have gone through many different phases or changes. That's one perspective that I try to emphasize in the book, is explaining the most modern incarnation of these ideas, but also looking back historically, because that's really important for understanding how we got to where we are now and the logical threads that led us to this place. So the way that I see it is the very early papers, we're looking around 2000, early 2000s. We're looking at a way of taking a lot of the work that was done in the 90s in unsupervised learning, latent variable models. A lot of this work was done by Jeff Hinton, Gahar Mani, David McKay, and others, many other researchers, and bringing that into the brain and looking at cortical function and cortical architecture, and seeing how there could be a mathematical description of the type of operations the brain is doing that would match, is well modeled by unsupervised learning. That led into a perspective of bringing the idea of action into this framework. And in the early papers around 2006, active inference and the free energy principle were kind of described together, where the free energy principle is much more of a descriptive term, saying, agents want to avoid physical damages to their physical structure. So being crushed or, undergoing what they call a phase transition. Like you don't want to experience a certain range of things that are permissible for your body's physical integrity. And so what actions do you take and what do you need to do as an agent to prevent disintegration or, just becoming part of the external environment? You're no longer different from the atoms and the rest of the atoms in the world around you. And then as the field evolved, those two terms sort of branched out. So around 2010, you start getting more of what we call active inference in continuous time, and you get a bit more of what is now called the free energy principle. But then as those fields evolved further, around 2015, you start getting more of the discrete formulation of active inference, which we can talk about the distinction later between continuous and discrete here. And then we also have the free energy principle becoming kind of this overarching philosophical and mathematical basis for active inference that later evolves into what's now called Bayesian mechanics around 2018. And so the way I see it from here, we now have three different strands that are kind of going out from this point onward that all interact with one another, but have slightly different sets of papers and formalisms that are associated with them, but are all unified under the same umbrella of this theme of free energy minimization.
So what is active inference?
Active inference then is so the application of the free energy principle to agents that perform perception and action. So these can be biological agents that have brains, human brains, animal behavior, and this view is, in the literal name, actively inferring. So everything under active inference is inferential, meaning that there is an unobserved or unknown quantity out there. What is the state of the world? And so that has to be inferred indirectly from some kind of sensation that these agents receive. And that inference process is perception. Active inference, and actually just to say this now, the inference process uses the free energy principle in that it minimizes variational free energy in that calculation. So that statistical quantity is the basis. In machine learning talk, it would be an objective function that we try to minimize, which will enable the agent to describes the behavior of the neurons or representation units in that agent coming to a steady state. So the behavior of those neurons as they interact follows a gradient flow on variational free energy. So it describes what that system is doing, its behavior. And that process of perception, which inherently relies upon free energy minimization, is taken to the next level with active inference to suggest that action itself is also a form of inference that also requires minimization of variational free energy. So I'm saying this specifically to underscore the idea that this property of free energy minimization inherent in the free energy principle is a component of both action and perception. And these are kind of unified together. They're not, under a separation principle, separate modules in the brain where you do one and the other. They're kind of linked together, and they're linked as one type of thing that the brain does, where action is a prediction or an expectation about the kinds of sensory information the agent expects to receive, and it controls its environment to bring about that state of affairs. So when you link these together, you get essentially what we call active inference, which is all written in this language of probabilistic models, where the optimal action or the optimal perception is described as a minimization of variational free energy.
It might be worth just meditating on this for a second. So in machine learning, we just have the perception bit. Mm-hmm. And it's also relevant that we just usually train once. So now we have perception and action linked together in what I guess Friston would call a cybernetic loop. Mm-hmm. But the iterative component of information sharing is really important. I think computationally, the reason why we can encourage the emergence of sophisticated behavior is because we have this iterative inference and information sharing with the environment, and that seems to set it apart.
Yeah, so you mean iterative in the sense of like online, like you're continuously learning as information is streaming in, and that's changing the model.
Yeah, that's right. Yeah. I mean, it's a similar thing to a cellular automaton. Mm-hmm. That's also iterative. So at every single time step, we are using the state from the previous time step, and then we're performing a computation, and we're iterating and iterating, and it's essentially an unbounded computation. Yeah. And that's a very, very different type of computation to machine learning, where you just compute a bunch of weights once, and then that's it. That's the end.
Yes, so that's a really good point. One thing I didn't mention in my description just a moment ago was the temporal nature of this. That's just inherent in these models. It's always assumed that the environment is dynamic, which means it's always changing. Now, if you are in this speaks to the idea of inferential learning, you can constantly keep updating these models. As new information comes in, if you're perceiving something different, that changes how your action is going, what actions you're going to take. So this level of control is really intimately linked to what you're perceiving, because if the state of affairs changes outside in the world, you're in a new location, something is new, you may have to perform new behaviors in order to reach back to this free energy steady state. And so this is a kind of iterative process, as you say. It takes place over time, and the dynamics is really important in these models. And it also kind of speaks back to some of the other topics we were just discussing, in that a very volatile environment, it may be hard to find that minima. But if you build in a lot of predictability into your environment, things that are very stable, things that are very predictable because you have cultural rules or rules about how the world operates, it makes it much more efficient and easy to find that minima because there's less things to consider as options in there.
Yeah, we don't need to meditate on this for too long, but of course in the ML world they do have reinforcement learning, and that also has this kind of iterative property. What's the rough difference between the two approaches?
So I would say there's a number of different differences in there. In that, for example, in reinforcement learning, the state action mapping is what your policies that you're attempting to determine what should the agent do in terms of what actions will bring it into certain states. versus the active inference approach is looking to compute using, as an inference problem, sequences or trajectories of actions. The agents, you can think of them as paths if you want to use kind of a physics metaphor of actions being these kind of motion paths over time. Then you can think of them unfolding in time and picking the right path to reach some sort of end goal state. And so that's what's called a policy. Sometimes it's better to call it a plan so that we can disambiguate from confusion with reinforcement learning. It's a plan of action sequences to execute at a given moment in time based on the information and knowledge the agent has in that present moment, combined with its preference of what it wants to, I'm using that anthropomorphically, but you could say expects to receive in the future. And so a component that I think really separates active inference and reinforcement learning is the appearance of this epistemic value term that appears in what's known as expected free energy, which roughly speaking is a way of using is a way of a function that you minimize for selecting policies in the future. So where information you don't have yet, because variational free energy is used for current and past information, expected free energy is minimized for future planning, picking out those plans or action sequences. And what's really important about active inference agents is they have the ability to forage for new information and look around for interesting and new information in their environment, and reduce the ambiguity that they have about their environment in order to increase the confidence that they can actually reach that goal state. So there's a natural level of curiosity and exploration inherent in active inference models that are part of the way that an active inference model, active inference agent functions.
Yeah, I mean, certainly in reinforcement learning you can do exploration, but I can appreciate it's far more principled if you do it in a Bayesian way, because you actually know where there are areas of uncertainty. When I spoke with Jeff Beck about this, he said that admittedly it was kind of similar to like a maximum entropy inverse reinforcement learning agent, but surely it must be more principled in other ways, though. It's a really good way of defining, states and agents and being able to design much more structure into the system rather than the inscrutability of reinforcement learning.
Yes, I think the key way that active inference looks at this problem is purely inferential. So it's sort of the planning as inference statement. All of the behavior that you see in an active inference agent does not require, ad hoc temperature parameters or other kinds of things that you do to tweak the system. The behavior just emerges out of the expected free energy equation itself. And so you have this idea of curious and exploratory behavior as a kind of inference in itself, where you have this long-term, incurring of uncertainty or exploration for the purpose of, in the long-term average, minimizing variational free energy for future states. So this sort of perspective on inference and the way that it's encoded in the model is different in the sense that from the way that it's performed in reinforcement learning.
Sanjeev, thank you so much for coming on. I really appreciate it.
Absolutely. Thank you so much for having me.